common knowledge that the moon is a cratered ball of rock. Stunning as it is in the night sky or in photographs taken from orbit, the landscape is barren, gray, dusty, and dark. Are there other things to be found than meets the eye? I'm Alana Bartolini from ESA Education, and joining me today is moon scientist Alexandre Maurice. Thanks for being here with me.
Hello.
Tell me, do we expect to find any other useful materials on the moon than dust and rocks?
So yes, an important resource at the moon would be the sunlight first, as we expect solar panels to power all our activities during our lunar exploration. The only issue is, of course, it's the cycles of day and night is very different at the lunar surface than what we're used to on Earth. If you are around the equators at the moon, you will have about 2 weeks of sunlight followed by 2 weeks of complete darkness. But if you go towards the poles, you will have sunlight all the year. And next to it, you will have permanently shadowed region, permanently shadowed craters, where craters which have never seen light in billions of years. So these are very cold craters. And actually, the temperature in this crater can go down to minus 200 degrees. And we think that water may have been trapped there, because as comets travel into space, some pieces may have fell into these craters over time, and the water which have fell would have accumulated in these craters. And we are not sure yet about the form of this water, but from the satellite images, we are pretty sure it's there. We have good evidence for it. If we could use this water, it would be an important resource. As the rest of the moon is completely dry, there is no atmosphere, there is no water. It's complete vacuum actually, but this vacuum can be challenging to deal with, but it can also be beneficial for some instrumentation. So it can be seen as a resource. And another resource could also you could see the difference of temperature, because during the day it's about 200 degrees at the surface, but during the night it's minus 150 degrees. So these changes in temperature, we can also use it to create electricity. But actually the real resource remains the dust and the rock. But it's not more than the dust and the rock itself, the resource is hidden inside, as these rocks are made of oxygen, are made of metals inside minerals, because the soil is what basically you can find is very similar to what you can find in volcanic region on Earth. And that's actually the real resource of the moon.
Okay, so how do we actually make use of these materials?
So this dust and these rocks, it's oxygen and metals strongly bonded together in minerals. And the idea is we develop processes, so it could be chemical processes, it could be gas processes, which enables at high temperature to extract the oxygen from the metal. Then we have oxygen that we can use for breathing, that we can use for refueling a rocket, for instance. And we have metals that we can use for manufacturing, for making tools and try to make construction elements. As of course we need a landing pad, we need roads, and for that we need to turn this dust into solid material. So we have also the processes for that. But these processes, for instance additive manufacturing, would be very useful for also shielding material, because you have constant radiation environment in space, you have radiation from the sun, you have radiation from space. So at the lunar surface you need to be shielded, otherwise long exposure to this radiation would be very harmful for the body of the astronauts. So all the habitat will have to be covered by a thick layer of lunar soil, and that's of course that will have to be consolidated, and there are also processes for that.
And so can these resources help us go beyond the moon, for example, if we want to go further into space?
Yes, so once we have, for instance, oxygen extracted from the soil, or if we can make use of the water that we find at the craters, then we can, in principle, refuel rockets in the vicinity of the moon that could help them to go further into space or bring more payload, as the gravity of the moon is 1/6 of Earth's gravity. So we could take advantage of this relatively low gravity to go further into space. But actually the real value will be the knowledge we acquire at the surface, as we will going to learn how to live off the land, how to be independent from terrestrial shipment. Because for the moon it's fine, we are about 1 week away from the Earth. But if we want to go beyond into space, we can't rely on Earth shipment every now and then. So we'll have to be completely independent, and that's what we want to learn at the moon. How to live off the land, how to really sustain exploration without counting on Earth.
And is this the type of research that you're currently working on?
Yes, so my work consists in developing all these processes to extract oxygen from lunar soil, or for construction, to turning this dust into some construction material. But actually, I'm working on identifying the knowledge gaps and trying to fill them, so we can take all these processes out of the lab and make them into space and make use of them into space for sustainable lunar exploration.
And can you tell me, how did you get involved in lunar research?
So up to my master, I have a background in material science. I had no connection to space. I did my studies in France, in Russia, and then I got an internship at the European Space Agency, and that's how I set foot in a lunar research environment. I followed with a PhD at the German Aerospace Center, and that's how I developed my expertise in processes for using lunar soil, and that's how I ended up at the European Space Agency as a research fellow today.
That sounds like a very exciting job. Thank you for joining me today.
Thank you.
If you'd like to learn more about moon research, stay tuned for our next episode about how we use these lunar resources in 3D printing. We can 3D print just about anything these days, from tools and buildings to cells and even food. But that's on Earth, where materials are readily available. What about in space or on the moon? Could we 3D print a lunar base? Let's ask a materials engineer. I'm Alana Bartolini for ESA Education, and joining me today is Advanit Makaya. Advanit, nice to meet you.
Thank you, Elena, for having me. I'm a materials engineer here at ESA, and I will tell you more about 3D printing on the moon.
Advanit, before we get to the big question of whether humans can 3D print on the moon, can you explain how 3D printing works?
So 3D printing is essentially how to make an object layer by layer. So you can think of it as you want to print a toy, or you want to print a cup, and you start to think about how it would look like if you slice it in very thin layers. So you would know how each individual layer looks on a sheet of paper, for example. You put that in a computer, and then you feed the 3D printer, the machine, with the material that you want to print. It can be a powder, it can be a wire, it can be a paste, and then the computer will tell your machine how to draw the slice of the part, exactly how it should look like. And you repeat it layer after layer. You make sure that the layers are glued properly together. And then slowly you see your 3D printing object being made. So that's how additive manufacturing or 3D printing works.
So do we already use 3D printing in space? How can this additive manufacturing be used in space?
So we are already using 3D printing in space. Not a lot, but it's already starting. For example, on the Ariane rocket, there are parts which have already been launched, parts of the rocket which were made by 3D printing. So that's something we know how to do. And here at ESA, we are working on parts of satellites which are made by 3D printing and which will be launched soon. So 3D printing in space will be a reality. 3D printing on Earth is something that we know relatively well. You can buy a 3D printer for your own house. You can play around, make some toys and so on. And if you've ever taken a plane, some parts of the planes are now 3D printed. So that's something that we know how to do. On the International Space Station, we actually have a 3D printer. We, ESA, have launched one about 4 years ago, but it went back to Earth, and NASA has a 3D printer permanently on the ISS. So the astronauts, the idea is that whenever they need something breaks, they can have it made directly on the station.
And how do you think we can extend 3D printing to the moon?
The idea is if you go to the moon and you are going there to stay, if you build a moon camp, at some point you will need to manufacture things. At some point things will break or you need to replace things. So rather than waiting for the next rocket to bring you your supplies, you could actually manufacture them on demand when and wherever you want on the moon. So that's how we are thinking about using 3D printing. And 3D printing really could be used to support anything on the moon, from the structure to build the walls of your habitat, down to the tools that you use, cups, screws, forks, and so on. And we even have techniques to 3D print food.
Can you tell me a little bit more about 3D printing food?
Yeah, so 3D printing food is about the idea of mixing all the ingredients into a big box, and then it flows through a tube, and you can give it the shape that you want. So you can print cookies, you can print pasta, you can even print fake vegetables out of different ingredients, different things that you mix together. So that's quite important for the astronauts because they will need some variety, different things to eat every day of the week, and they only have a limited number of ingredients that they can use. So we can make funny shapes, we can make funny colors, so that their life is a bit nicer up there.
So speaking of these kind of innovative ideas, what's the coolest thing that you've ever 3D printed?
So the coolest thing I have 3D printed, or I've made 3D printed in one of my activities is in ESA, is probably this little astronaut, which was 3D printed using the lunar soil, the dust that you find on the moon, and you can get very fine shapes. So that's pretty cute. We have also 3D printed cookies, so I haven't tested them. But that's something
hopefully not out of the lunar soil.
Not out of the lunar soil, but that's something pretty cool as well, and that just tells you the possibilities that 3D printing offers to make life a bit nicer on the moon.
And how did you get interested and start working in materials engineering?
So when I was at uni, I didn't really know what to do, but what I knew is that I like to understand how things are made, how they work, how do you make them. And slowly I've grown an interest for materials, and I decided to spend most of my time working on that.
Thank you for joining me today at Beneath.
Thank you, Elena.
Stay tuned for our next episode to learn about living on the moon. The Apollo missions proved humans can work on the lunar surface, but the longest lunar spacewalk lasted a total of 22 hours. Could humans spend longer amounts of time on the moon? How about live there, as they do on the International Space Station? I'm Alana Bartolini from ESA Education, and here today with me is lunar technology expert Bérengère Audoux, who's going to join us to talk about life on the moon. Welcome, Bérengère.
Good morning. I'm very happy to spend a bit of time today with you talking about living on the moon. This may sound a crazy idea, but this could be possible sooner than we think.
So tell me, Bérengère, what are the main differences between living on the moon and on Earth?
There are many, but I will concentrate on three main ones I can think of. First of all, one of the most obvious differences between the Earth and the Moon is the fact that the Moon has no atmosphere. And no atmosphere means no blue sky, no air to breathe, no life, no weather. You cannot go simply outside on the Moon. You need to wear a very well designed and pressurized spacesuit. It's a sort of mini spacecraft all around you. The second difference I would like to point out regards gravity. If you weigh 30 kilograms here on Earth, on the Moon you weigh only 5 kilograms. As experienced by the Apollo astronauts, walking around on the Moon is not that easy and takes actually quite some time to get used to. They developed a sort of bunny hop in order to be able to move around, and this method basically helps them not to fall over when they were going forward. Harrison Smith, who is the last man that walked on the moon, said actually it was like walking on a giant trampoline. Quite fun, probably actually. Since your muscles will not be as stimulated as on Earth, you will need to plan a very thorough and intensive exercise daily training in order to avoid to become a couch potato. The last difference I would like to tell a few words about is about the temperature range. Since the lunar surface is relatively dark, its reflectivity is about the same as the open ocean here on Earth. And since you have no weather, no clouds to cool the surface, during the day, the temperature on the moon can get to 120 degrees. It's extremely hot, of course, you can realize. And that's why the Apollo astronauts only went out on the surface, outside of their module, in the morning time, in order to make sure the sun would still be low, we're talking about 15 degrees, so that they don't get too hot and their systems are operational in standard conditions. As dangerous, actually, is also the fall of temperatures during the night. And during that time, it can get until minus 135 degrees Celsius, so well below frozen temperature. And it's also important to be aware that on the moon, the nights last actually 14 Earth days, and the day is the same. Last but not least, you would have an amazing view of the Earth from the lunar surface. The Earth is indeed 3.7 times larger than the moon, and it covers over 15 times as much of the skies as the moon does when you're looking at it from your bedroom.
So in the future, will humans be able to live on the moon for longer periods of time?
Very good question. After 50 years since the American with astronauts and the Russian with robots reached the lunar surface, the moon is finally again a destination of very high interest. This new discovery is opening new perspectives when thinking about living on the moon, because in that case, if it's true, we will not need to bring with us everything from the Earth, and we will be able to live from the land in a way. And actually, many people around the world are working on it. Engineers, scientists, doctors, politicians, and so on. Humans will not live on the moon for a very long time on the first go. I don't believe so. There will be a first build-up, progressively setting up on the surface, with stays starting with a few days, then evolving to a few weeks, and finally months, hopefully. This will allow the astronauts to get acquainted with the very extreme environment of the moon, as we already discussed before, and as well to set up progressively all the necessary supporting systems and infrastructure, a bit like basically we did when we were exploring and starting the exploration of Antarctica. Living on the moon for a long time will only be possible at very specific locations on the moon, which today are actually still unexplored. And I'm talking particularly over the South Pole region, which presents very specific characteristics of illumination. There you can find places at quite some higher elevations where the sun shines over 90% of the year, which is of course very favorable from a solar energy point of view.
Now for a question I think many people would like to know. Could there be an actual moon village in the future?
A lunar village in the sense of a human community of a certain size, living and working on the moon in a sustainable manner, will ask for a completely new lunar way of life. It means developing and using innovative, smart, new space systems, developing new capabilities in the area of radiation protection, in the area of food, water, oxygen, carbon dioxide management and recycling, and all those topics being actually also of very high interest for here on Earth. People are already living in space. I'm sure you have already heard about the International Space Station around the Earth. And of course there are already a specific system helping with what we call life support to help the astronauts live and survive in space. For instance, one of them is about taking the carbon dioxide exhaled by the astronaut, concentrating it, and then breaking the molecules in order to recover the oxygen part. So such type of systems will be needed for a long stay on the moon, even more performance, and possibly combined with other recycling loops, like for instance to support the growing of plants for food production and so on. At the end, the moon is our closest neighbor, still about 400,000 kilometers away. And as such, there we can test new technologies, we can gain knowledge, we can set up new science infrastructure, and in that way prepare our travel to even further destinations in the solar system.
Bérengère, did you ever dream of living in a moon village? And how did you come to work in lunar exploration?
Yes, I often dream about becoming a moonaut. But it will probably not be possible for me, maybe for you. And I actually started working in space already at the very beginning of my career. And I worked on systems to help astronauts, training them before they go to the International Space Station in terms of orientation, helping with designing spacesuits and so on. And then I evolved towards studying a mission, fully European, going to the moon, from launching from the Earth until operating different scientific payloads on the surface. And that's where basically I caught the bug for lunar exploration. I enjoy very much working every day on developing new technologies for exploration and expanding our knowledge of the moon. And this actually with numerous men and women in Europe, but also in the world, engineers, scientists, and so on. There are many different jobs to make living on the moon become true. And why not one for you?
Sounds like a very exciting career. Thank you very much for joining me today, Bérengère.
You're very welcome, my pleasure.
If you enjoyed this episode, stay tuned for our next one all about the future missions on the moon. Though it's been 50 years since humans first stepped on the moon, we haven't forgotten about Earth's natural satellite. Several missions since Apollo have taught us so much about the moon and have paved the way for humankind's return. I'm Alana Bartolini from esa.int, and here with me today to tell us a little bit more about these missions and future exploration of the moon is Dr. James Carpenter. James, thanks for joining me.
Hi.
So to start off, can you tell us a bit of a summary about moon exploration so far?
The moon, of course, is our closest celestial neighbour. It's something that humans have looked at and tried to understand forever, right? But then lunar exploration really began in the 1960s and 70s, where we had robotic and human missions going to the moon. From the lunar missions from the Soviet Union, which roved around on the surface and returned samples. But then really the pinnacle of this was Apollo, and the first and only time in history that humans have set foot on another celestial body. Now that was not a scientific program. It wasn't done to create new scientific data. It was done for a whole set of other reasons, but at the same time, it was really transformative for science. So what we learned from the samples that came back from the moon was the origin of the Earth and the moon as a system that has a common origin. We learned that the moon has been an archive of solar system history, that the moon is the only place where we can go to learn about the history of our own planet, especially in the early periods that have been lost from our own terrestrial geology. So this was really transformative for our understanding of how planets form and evolve, and become the basis for planetary science and much of what we know about our own planet too. So that's something which started in Apollo and has gone on since then. So people are still using the samples that came back from Apollo 50 years ago to do new science. And that's something that's really taking off again in the present time in recent years. At the same time, after Apollo, we had this period where not a lot happened on the moon. It was very quiet. There weren't any missions there. The moon was quiet once again. And then the last few years, we've had this renaissance of lunar exploration. We've had new missions from the United States and from Europe with Smart 1, and then more recently from China and from India and Japan. And so these new missions have created a wealth of new data, which have really given us a global context for what came before. So we're now starting to understand everything that we've done before with these samples and these early missions to the surface, but really in a global way, finding out what this means in a broader sense and how we can interpret that better. It's also taught us that even though all these samples, all this science that was done in the past is the basis of so much of what we understand about the history of the early Earth and the planetary formation in general in the solar system, it's very incomplete. That the moon is a large place, has tremendous diversity. We've really only scratched the surface.
So taking all of that into account, what are the next steps? What's in store for the future of moon exploration?
So I think what is coming is very exciting. We have multiple countries, multiple agencies, and people outside of agencies in the private sector, people who are not from space agencies, but really have their own either businesses or their own fortunes, people who are very, very wealthy, who are trying to explore the moon now. India tried to land this year. They didn't succeed, but they have an orbiter now going around the moon and they plan future missions. A private sector mission from Israel tried to land on the moon earlier this year, was not successful, but that also was the first time a private sector company had tried to get to the moon. We have missions from China, so China landed on the moon this year, the first ever far-side mission, and they have big plans for the future, involving the establishment of a lunar research station, robotically initially, and then moving to humans over the next decade or two. And then in NASA now, in the US, we have the Artemis program, which is intended to bring humans to the lunar surface again for the first time since the Apollo era, and this time in a different way. So we'll be looking at doing science, exploring places that have never been explored before, but also exploring things like how we can use the local resources that we find on the moon to enable permanent, sustained and sustainable exploration to learn how we as a species can live and work away from our own planet. And we in Europe have a vision for exploring the moon, which is one about partnership and cooperation. So we want to deliver science, we want to prepare the future, we want to create the technologies and capabilities by integrating science and technology together that prepare us for exploring the solar system beyond the moon, but also establishing sustainable exploration of the moon for the benefit of humanity. And so we are working in particular with the United States, with NASA on the Artemis program, and we're very excited about the contributions that we're making to that and the developments that we're making in the coming years.
So one of the questions or things that we sometimes hear is, why are we going back to the moon? What are some of the reasons that we should continue exploring the moon?
Okay. So the moon is an archive of solar system history. On Earth, we have plate tectonics, we have water erosion and wind erosion, and this has removed the earliest periods of geological history of our planet from our own planet. Now the moon has remained geologically very stable for a very, very long time. And so as the sun has changed over time, as comets and asteroids have bombarded the inner solar system, as our solar system has moved through the galaxy, going through the spiral arms, through dust clouds, near supernovae, all of these events have had an impact on the inner solar system, and all of these events are recorded somehow in the surface of the moon or in the moon somewhere. And so by accessing the moon, we can find out about the history of our solar system, of our own planet, and about all of the things that have happened there over eons of time that have been lost from our own geological record. At the same time, the moon is a place where we can learn what it means to live and work off-world. So there are resources on the moon that we could conceivably use. So we now know that at the poles of the moon we have very, very cold places that never ever see the sun. And these are some of the coldest places in the solar system, and we know that in these places now we have water, ice, and other we call volatile chemistry. This is the chemistry that creates the building blocks of life, but it also can be useful. So water is oxygen and hydrogen. Oxygen is useful for humans, and oxygen and hydrogen together are rocket fuel. So we could conceivably have a store of fuel at the surface of the moon that we could use to explore beyond. At the same time, the minerals around the moon are made of oxygen, metals, and silicon. And if we could find a way of separating those things, then we have oxygen, which again is useful for life support, but also for propellant, for fuel. And we have metals and things we might be able to use for manufacturing on the surface of the moon. We go to the moon to understand the moon and what it can teach us about planets. We go to the moon to understand what it can tell us about the history of our solar system and our galaxy and our star and the planets in the solar system. We go to the moon to understand the origins that we share between the Earth and the moon. And we go to the moon to use that as a platform to look outwards beyond. And we go to the moon to understand how we as a species can live and work off Earth in a sustainable way to prepare future exploration, but also to understand better how we can live and work sustainably here on Earth.
And so, James, you're a moon scientist. How did you get started in lunar research? Did you think that you would be working to get humans to go back to the moon?
So if I told my 9-year-old self what I was doing now, my 9-year-old self would be very excited about it. I think that when I was a child, I was really excited about space and exploration. And then I reached my teenage years and it stopped being something that had any meaning because I didn't see this as something that was realistic. It was a childhood fantasy, if you like. And then it wasn't really until I was about 16 when I suddenly realized that this was a real thing. That even here in Europe, there were people that did this for a career. There were things that were happening here. And when I learned that, I had to do it. So I studied mathematics, physics, and chemistry at A-level, which were the qualifications we had in the UK at that time. And then I went on to study physics with space science and technology for a degree. I did my PhD, and then after some years working on space projects in the UK, I came to the European Space Agency to support future exploration missions. And I think now is a really exciting time to be here and working on this because I think we are at the beginning of something that is going to be very exciting, very future looking, which is really going to be international and where Europe and we in the European Space Agency and where the people of Europe can be very, very involved. And I think if you are a student or a child today who is interested in space, there has never been a better time because when you are leaving school and when you are going into the workforce, these are the things that are going to be happening. We are going to be going to explore the solar system. We'll be doing that as a species in cooperation, and there are extraordinary opportunities waiting for you.
And with that wonderful sentiment, I want to thank you for being with us here today.
Thank you.
To all of you watching, thank you very much for watching this series. I hope that you have enjoyed learning about the moon with our ESA experts.
Hello world, my name is Stijn Tolen and I'm ESA's research doctor here at Concordia Station in Antarctica, and I'll talk with you a bit more about how it is to live in isolation here. So Concordia Station is one of the 3 stations in the middle of the Antarctic ice sheet operating year-round for science. For a 9-month period within this year, it's not possible for any transport to get in or go out of the station because of the extreme conditions outside. So I arrived here 5 months ago as part of a 12-member crew to stay for this winter period to maintain the station and continue with science. The main goal of my mission is to implement biomedical research experiments on myself and on the crew. And these experiments have been selected by ESA to learn more about how this environment can be a risk to our body and our mind. You can imagine if we want to plan for future manned missions to the Moon or to Mars, it's important that we understand these risks better. Because if we go to space, we have to deal with all kinds of stressors. Deviations from the normal situations, you could say, that ask our body and mind to adapt. And this can have quite some consequences for our health and also for our performance. Think, for example, about bone and muscle loss, if there's a lack of gravity, or space radiation, if we go further into space. It can have serious long-term consequences as well. But also not being able to just go back home if you want to. Being isolated and confined in a small crew and not being able to go outside because the conditions outside are too hostile. This is where Concordia is interesting. So Concordia is quite such an environment. Here we live with 12 people for 9 months without any possibility of rescue. And we are at altitude, so there's less oxygen to breathe in the air. And outside temperatures can go as low as minus 80 degrees at one point, and there will be a time period of 3 months without any sunlight. So in that sense, Concordia classifies as we call it, isolated, confined and extreme environment, which has many similarities with space. It looks a little bit like living in a future space habitat. So the experiments that we're going to perform this year here look into changes in blood volume, changes in our immune system and in our gut bacteria, and how they can impact our health. But also we look at eating behavior, sexual feelings and well-being, and mindfulness, which can maybe be helpful to help us adjust to a strange environment like this. So prolonged isolation can have a psychological effect on us if we fail to fully adjust to this new environment. And you can imagine that's not so easy. It has been described in people that overwinter in Antarctica that they can develop symptoms of tiredness or headaches or sleep problems or problems with attention and memory. But also you may start to feel depressed or more anxious or angry, and there may be conflict between people in the base or even with people back at home. Usually you see that these kind of symptoms are more present during the harsher middle of the winter when the stressors are higher. But if we then talk about long-term effects, you also see when the stresses get lower, when for example the sun comes back, the symptoms get less as well. So we call it therefore the winter over syndrome. But most important, I think, is that overcoming and sharing these challenges together of overwintering in Antarctica can also come with a sense of accomplishment. And you see that people going to Antarctica often see this experience as a very important one in their life. It can come with more self-esteem, we may become better in solving problems and even feel closer together and get a better understanding of each other. And to me, this is the reason that I came here, because I think this is a very valuable experience. Living in isolation, personally, I think it can be helpful to try to create an environment that is a little bit more like at home. So for example, here I try to maintain a daily rhythm that mimics the day and night, even if there's no sun outside. And I try to stimulate my body with exercise, even if it's not possible to go outside and do my favorite sports. I also try to keep eating healthy with the idea that all these stressors is something our body needs to deal with and it could use some good food. Staying in touch with the people at home, with my family and friends, for me it helps a lot. And sometimes I actually do go outside, for example when I've collected samples, such as stool samples, saliva samples, blood samples, and these samples need to be stored cold, so lucky for me that I've got a big freezer outside. But more important maybe is also to understand that even though this is a new environment, it doesn't necessarily need to be an unpleasant one. I try to focus on things that I can enjoy myself with during my time here, such as new hobbies, and I might set new goals. And then if we are living with other people, especially if those people are not the ones you choose to live with, like here, I think it's important to be very tolerant as much as you can. And it's not always easy, especially when the stresses are high. We tend to think first about ourselves. But to look into the perspective of the other person, I think here is very important.
My name is Jérôme Benveniste. I studied math, physics, earth sciences in Paris, France, my home country. And I did a PhD specialized in oceanography from space in Toulouse. Most of the instruments we use in remote sensing are common to space exploration and Earth observation, and this is not surprising. What is remote sensing? It's just like, say, you want to know if the fire is hot. You don't need to touch it. You just put your hand in front, and without touching the fire, you feel it's hot. That's remote sensing. If you shine light on an object, your eyes receive the reflection of the light, and you see the shape and the color of the object. That's remote sensing. The sense of touch is much different. You need to touch to feel what you touch, so that's not remote sensing. Using the analogy of the ears and the eyes, we develop instruments that we use both for outer space and Earth remote sensing. And it's based on the electromagnetic radiation, either in the microwave band, like the cell phone frequencies or the microwave oven, or in the visible band, or infrared or ultraviolet. And this is why, if you learn everything about remote sensing, you can study the Earth, the solar system, the galaxies, the universe, and even beyond. Earth observation satellites go around the world in 1 hour and 20 minutes, so it's much faster than an oceanographic ship. It also repeats and repeats, and the observations are made for many years, typically 5 to 10 years. So you can imagine how fast we can acquire knowledge about the ocean, such as sea level, wind, waves, currents, temperature, salinity, thanks to gravity, and also the presence of algae and plankton. The ocean is vast and deep, and by snorkeling or scuba diving, you can take a look at the first 10 to 15 meters. But the ocean is 11,000 meters deep, so it's 1,000 times more. So making soundings from a ship is like launching a rope with a hook from a hot air balloon from above the clouds, and probing to see what you can catch, like vegetation, a bicycle, an old tire, an umbrella, a cow, whatever. But from that, it's really hard to recompose what is exactly at the surface of the Earth. Well, it's the same for the ocean. And if you dive deep, like 500 meters, because of the pressure of the water column, you will need to decompress and on your way back. And that has to be done slowly, and it can take up to 3 weeks. So it takes 3 weeks to come back from 500 meters deep in the ocean, and only 3 days to come back from the moon, which is 800,000 times farther. And, it's 500 times the atmospheric pressure. Well, since the space era, we've been measuring sea level worldwide, globally, and before that, sea level was only measured by tide gauge in ports and just along the continental coast and in the open ocean at islands, but not everywhere in the world. With radar altimetry on satellites, we've been recording that sea level is rising. That's about 3.2 millimeters per year on average in the past 27 years. Well, thanks to the global picture that we can make with satellites, we can see that sea level is not rising everywhere. So this is a regional map of the mean sea level. So the resulting sea level rise on average is creating a much higher flood risk in case of storm surges, and severely impacting the coastal and island communities through damage to coastal infrastructure, the agriculture, and even tourism and recreation activities. The World Ocean Day is taking place annually on 8th of June, and it fosters the public interest in management of the ocean, managing its resources, and keeping us on track with implementing the United Nations Sustainable Development Goals. And so keep an eye on the ocean at least once a year on 8th of June, and of course every day, because the ocean is supporting life on Earth. Once we have mastered the measurement of sea level in the open ocean with radar altimetry, we've put the limit to measure the sea level near the coast, which is more difficult, and in the estuaries, then in the deltas, and we went up in the rivers and lakes. So river discharge is really an important, what we call essential water cycle variable to understand the effects of global change. river discharge monitoring, day by day, is not only for climate, but it's also for predicting floods, which is the most destructive natural catastrophe. In the European Space Agency website at esa.int, you will find almost all the answers for which you have curiosity. And the ones that are not answered are the most fascinating ones, in fact, and we count on you to help answering them. And so have a nice time using space.
My name is Sara Morales Serrano. I'm system engineer for Clean Space, and today I'm going to try to explain you what is the problem of the space debris and what do we do at ESA to solve it. So space debris is any man-made object that is in space and that is no longer functional. As you know, we have been sending spacecraft to space since the 60s when the spaceflight started, and not all of them have re-entered and have left the space free. So there are two main orbits that we occupy with these satellites that are the low Earth orbit, what is considered one important region that is highly populated, and there we send our mission, for example, for Earth observation, where we can see how the Earth environment is evolving, or we can do, for example, weather prediction to know which is going to be the weather tomorrow. But also there is other orbit, like for example the geostationary orbit, that has some characteristics that are very particular, that they are all the time on top of our head. So they are very good for doing telecommunication, so for example to have our TV at home, or to use our mobiles. Nowadays we have 5,000 satellites, more than 5,000 satellites in space, and only 2,000 of them remains operative. We have lots of rocket bodies, so parts of our launcher that have remained in space, and some events have created even more debris. These events are, for example, collision between two spacecraft that have generated a big cloud of debris that is orbiting the Earth, or also some other events, like for example, self-explosions of our satellite. How do we take care of the environment here on Earth? So what we do is to try to assess all the environmental impacts of our missions during the whole life cycle of our mission. So since the beginning that we are developing our missions until the end of life. And we take into account all the phases like manufacturing, the launch of the spacecraft, and also the operations of our mission. So for this, we use a methodology that allows us to calculate what are the environmental impacts here on Earth. Like for example, in climate change, all our emissions that we have to soil and also to the water, and all the possible toxic materials that we use in our spacecraft. And the aim is to try to find alternatives that are greener and then they are polluting less to the environment. We also try to take into account the environmental impacts in the orbit. So for this, what we do is to try first to reduce the number of debris that we are creating and to remove the ones that are already there. So first of all, what we need to do is to leave free this space of the orbit, so remove the debris from this spot that was occupying during the lifetime. And we have requirement that states that we have to re-enter in the atmosphere in less than 25 years after the end of life. This is for the low Earth orbits, but also for the geostationary satellites, they have a similar requirement to go to a graveyard orbit. As we said, we want to stop creating debris, so one important requirement that we have to follow is to deplete or empty our source of energy that we have in our satellite. So for example, the batteries, to make sure that they are empty at the end of life, so they will not explode. This one is also a requirement, and also another one that is very important to follow, that is we don't want to have any risk when a satellite or debris is coming back to Earth. So we don't want that it falls in our roof and it causes any damage to us. So we have different requirements depending on the size of the satellite. If we are a big satellite, we will go to an uninhabited region in the Earth. Or otherwise, we try to maximize the disintegration during the atmosphere. So we design our satellite in a way that will disintegrate faster. We still need to do some actions in order to prevent the creation of more debris. And there are studies that show that we have to remove at least 5 large objects per year in order to stabilize the situation. For this, we have been studying during the past year several tools that allow us to remove the debris that are in orbit. Like, for example, the nets that are like a fishing mechanism. It works in the same way. So we will drop a net around our spacecraft of our debris. We will grab it. It will be enclosed inside this net, and then we pull it back to the Earth to burn up in the atmosphere during the reentry. Another tools that we have studied is an harpoon. We shoot this harpoon against the satellite, so then it will go through it, it will capture it, and then we do the same way. We will re-enter our spacecraft. Then other tools that are more sophisticated and can help us to do future servicing in orbit could be the robotic arm that will go closer to our target, it will grab it, and then once it grabs it, it will bring it also back to the Earth to burn up. These are several tools. There are many more that are under study. And now at ESA we have our first mission that it has been announced, that it will go to grab one of these part of the launcher that is in space. We will grab it and bring it back to Earth. So as you can see, there are many things that we need to do. We have to start now, and this is what we are trying at ClearSpace.
Hi there, my name is Belinda Rich. I work in ESA's Advanced Concepts team, focusing on advanced materials for space habitats, and I'm here to talk to you today all about the Advanced Concepts team. So the Advanced Concepts team, or the ACT as we like to call it, is ESA's team of future concepts researchers, and that means we focus on new concepts that could be applied to solving problems in the space sector many decades from now. Our job is to both monitor the current research and perform new research that could either be in space concepts that are too distant in the future for ESA to be focusing on right now, or in topic areas that don't currently have a link to the space sector but have the potential to be. What makes our team unusual is that we are made up of scientists from many different scientific backgrounds. So, for example, currently we have computer scientists, mathematicians, architects, physicists, biomedical engineers, mechanical engineers, and more in our team. Because the ACT is made up of a team of very diverse scientific backgrounds, we are never focused on just one topic. Instead, we are always running multiple studies and projects at the same time. Some of these research projects may look a little different depending on the topic itself. So some of the research will be performed in a laboratory. Some of the research may be testing concepts in a computer model or a simulation. And also sometimes we like to work with universities or research centres from all around Europe to draw on expertise from outside ESA as well. But always we are exploring how our ideas can be adapted to a space context. And sometimes that can happen in very surprising or unexpected ways. For example, an ACT study that I am currently involved with is investigating how we can best build structures on the moon using geopolymer, which is a concrete-like material that uses lunar dust as its main ingredient. In the study, we found that adding urea from astronaut urine to our recipe greatly reduces the amount of water we need in our recipe. And that's an example of how sometimes a great solution can come from an unusual or an unexpected place. A really exciting thing about the ACT is that a lot of the topics we focus on might not be what you expect from a space agency. For example, some of our team investigate technologies inspired by nature or biological process, and this is a topic called biomimetics. Inspiration from nature can come from the smallest places. One ACT project is investigating how plankton in the ocean use nano-sized light-trapping structures to increase how much sunlight they can absorb. The same idea could potentially be recreated to increase the efficiency of solar panels on our spacecraft. Another biomimetics project is simulating the movement of aquatic animals like fish to see how a robot might copy that movement to move through a liquid using as little energy as possible, which could come in very handy for future robotic exploration, with the possibility of liquid oceans in our solar system, for example, maybe on the moons of Jupiter and Saturn. Moving away from the natural world and towards the digital world, the ACT has also been investigating artificial intelligence by training simplified brain models known as neural networks to perform certain tasks. Using these networks, ACT researchers have been able to teach a drone how to pilot itself to a given location in the most efficient way possible. And this means that spacecraft like satellites could use artificial intelligence in the future to navigate, despite their very small computing power. But another ACT study is investigating how we can process lunar dust to create thin structural fibers known as lunar basalt fiber. These fibers have the potential to be manufactured in space without any humans present. Then, robotic winding machines can be used to build vast structures out of these fibers by winding a fibrous shell that could be large enough to fit a habitat or another structure. And this concept shows how robots could potentially build on the moon with no humans present at all, and without needing to send any resources to the moon from Earth. We even delve into concepts in fundamental physics and quantum field theory, where the ACT researchers have applied a technique called time frequency analysis, a concept which is already used in signal processing, which is important for satellites, to give a new picture of particle detection in a vacuum. This novel technique represents particle detection using time on the x-axis and frequency on the y-axis, which is quite similar to how you represent musical notes on a musical score. With this technique, instead of helping us to write a song, it's helping us to understand the behavior of the universe's fundamental particles. These are just a few examples of our recent research, but the ACT also investigates topics in mission analysis, neuroscience, energy systems, advanced materials, and even more. The Advanced Concepts team provides ESA with the capacity to always be exploring potential space benefits of advances made in science and technology. But one thing all ACT projects have in common is that they deliberately look outside the scope of ESA's usual work. While our job in the ACT is not to predict the future, we are helping to prepare and enable lots of potential futures for ESA and the European space sector. And it's those future technologies a few decades from now that our young people today will be using to push the boundaries of space.
Hello, my name is Nora Peterson and I'm a sports scientist. I work at the Space Medicine Office at the European Astronaut Center in Cologne since more than 15 years, and I have supported a lot of European astronauts on their mission to the space station, providing exercise and countermeasure regimens in order to prevent muscle and bone loss and to maintain physical fitness in microgravity. Gravity is a strong force that is with us all the time, but we don't realize it because we are used to it. However, if gravity is gone, then the sensors in the body realize that the gravity pull is no longer working and a lot of systems in the body get out of balance. Therefore, for example, astronauts in the first day on the space station see the puffy face because blood and lymph liquid gets pulled upwards towards the head until the body regulates this and normalizes the blood pressure again. However, this is an adaptation mechanism that happens only in space. It needs to be re-regulated once astronauts are coming back to Earth. The same happens also with muscles and bones. Muscle and bone, usually used to move around in a gravity field, acting to forces and carry weight, are no longer needed in space because the astronauts are floating. Therefore, astronauts need to train every day to maintain and to remind the systems to keep all these functionalities because the body needs to be able to return into a gravity field. And this is why we perform the daily exercise countermeasure training for the astronauts, to remind the body that bone and muscle are still needed in an Earth life. Muscle and bone need to be worked and need to be trained in order to be strong and to maintain strong. This is even the case on Earth, and people that don't work out regularly usually suffer from health problems that are related to immobility and also to weak muscle and weak bone. So even on Earth, if you don't work the muscles, it impacts your health. And on space, this effect is much stronger. So this is why it is so important that the training in microgravity is implemented. Astronauts spend a lot of time training in classrooms and also in simulators to learn the theoretic background, but also to learn hands-on how to deal with the different systems and how to react quickly. But also how to prepare experiments accordingly so that the science quality is still sufficient for the standards here on Earth, because they are the only ones that can implement these experiments on the space station. In the last week before their flight to space, the crew members are isolated from most other people in order to prevent them traveling sick or to bring any foreign germs or anything undesired to their crewmates on the space stations, since the crew that is on the space station is, due to the isolation, also more vulnerable to external and foreign germs. So they have to deal also with this isolation, which I guess we have learned by now as well, was how difficult this can be sometimes, in order to protect themselves against these intruders. So it is mental and physical preparation that is really important for the astronauts in order to prepare for the mission and to be ready for any event, even scenarios, because they need to be on their own, able and capable to deal with this on the spot and to be also able to healthily return to Earth afterwards. Astronauts are preparing for dealing with confinement and extraordinary external conditions, for example by performing expeditions in caves or in submarine stations like the Nemo in Florida. In this case, they learn to be highly self-efficient and autonomous even if help is far, and they need to be able to do their work even under difficult circumstances. How will the preparation change once the missions get longer and farther away from Earth? Definitely the organization of the missions will be different for these kinds of exploration missions. For example, the communication will be much longer between the spaceship and the ground. It can, depending on the distance, take several minutes until the answer can be expected. So this needs to be organized also in the way how the crew is communicating and organizing their work. Also, the space vehicle will be much smaller compared to currently on the space station, and the astronaut need to be well trained on the devices that will be available on these small space stations, and very skilled and knowledgeable to use them to the full extent to get the maximum benefit for their body to protect against the effects of microgravity, which will be still as strong as they are currently now. Being on a space station is still a very protected place. The Earth is near, and in case of an emergency, the crew could be quickly evacuated to Earth and return within a couple of hours. At the same time, the space station is still within the Earth magnetic field and protected from the cosmic radiation, which would be different for a trip to Mars, because the radiation in strong dosages can be dangerous for our body because it may destroy or even alter body cells and can cause DNA changes or cancer. So therefore also here technology solutions need to be found in order to protect the body from these high radiation dosages.
Hello, my name is Andy Shepherd. I'm a climate scientist. I work at the University of Leeds in the UK, but I also work closely with the European Space Agency. So weather and climate are very different things. The easy way to think about the difference between them is just time. So weather happens to us on a day-to-day basis, and one year on today's date it might be snowing, and another year it certainly won't be. And so the things that happen on short time periods are the weather that affects us, whereas the things that happen over long time periods, longer than seasons, so maybe decades or even longer, they're climate. And it's difficult to separate these effects from climate data records, whether they're collected by a thermometer on the ground or by an aircraft in the sky or by a satellite in space, unless you have a long-term record. And that's what we aim to do, have many decades worth of measurements of whatever parameter we're measuring, so that we can separate out the effects of weather and climate. And it's important to be able to do that because weather is quite erratic, but also is a very large signal that changes quite significantly, and often the climatic changes are much smaller. So you'll be familiar with Earth's temperature change over the past century is really a fraction of a degree centigrade or just over that. And that's a hard signal to detect when we have 20 or 30 degrees centigrade change in temperature on the planet each year. And we need long-term records to be able to do that. That's where the cryosphere helps, because it changes quite rapidly, even if Earth's temperature changes by only a small amount. So small changes in ocean or air temperature in the polar regions will cause ice to melt. And the easy way to separate the effects of weather and climate in the polar regions are just to think really simply about snow and ice. Snow is generally what we would consider to be weather, whereas ice is the long-term storage of snow as it compacts and moves through glacier systems. And becomes part of the climate record. And if we see changes in ice on Earth today, then they tell us about changes in climate. Antarctica has told us actually a huge amount about climate change in recent decades. So what we found is that parts of the Antarctic ice sheet are flowing too quickly into the oceans because the ocean around them is too warm, and that's causing them to be unstable. At times that causes ice shelves to collapse and break away from the continent and drift out into the Southern Ocean. And at other times it causes glaciers to speed up and to move more ice out into the oceans than can be replenished by the snow that falls inland. And that causes a difference in the amount of ice stored in the continent. And that really is simply just a difference in sea level rise, because that ice ends up in the oceans. And then anybody around the planet that has a coastline or visits a coastline or depends on a coastline for parts of their lives is affected by that. And we're instantly affected by ice losses from Antarctica, no matter where we are around the planet. So it's really important for us to, first of all, understand how the Antarctic ice sheet is changing, but more importantly, to be able to predict how the ice sheet will change in the future so that we can plan our lives around that. We've learned a huge amount about the polar regions thanks to satellites in space over the past 30 or 40 years. Some of the iconic stories that we've learned about are retreat of sea ice in the Arctic. That's been progressive during the satellite era, loss of about 10% per decade. Melting of the Greenland ice sheet, and in some cases extreme melting in very hot summers, and acceleration of Antarctic glaciers. And we've learned about all of these things thanks to satellite measurements. People have visited these places, but it's actually really challenging to be able to monitor the polar regions in anything like the level of detail that's required for several really obvious reasons. First of all, it's a very inhospitable part of our planet. It's cold almost all year round, and it's dark for half of the year as well. So it's really difficult to even exist in these locations. But more importantly, they're vast. They're huge places that can't realistically be monitored on the ground, on foot certainly, from the air or from ships even, because they can't travel over sufficiently large distances to be able to monitor the signals of change, which are affecting huge parts of these areas. So we depend heavily on satellite measurements to be able to monitor in all weather conditions. Well, we've got a great deal of gratitude to the European Space Agency and other international space agencies for two things. The first one is for designing and launching missions into space, and they started that many, many decades ago. It takes typically 10 or 20 years to even get an idea for a satellite mission off the drawing board and into space. And it's thanks to people that were designing these sensors in the 1970s that we had records in the 1990s and that we can look back on them. But the space agency is doing more than just that. They're creating and have been for some time now fundamental climate data records of how our planet is changing from day to day, from year to year, and from decade to decade. And it's only thanks to these high quality and long-term records of climate change that we can put together the jigsaw puzzle of how our planet is changing. In the polar regions, it's become really, really essential to have these measurements and the long-term measurements. So we rely upon these measurements more than you might think to be able to predict how sea levels will change in the future and how much more our planet will warm in the future, as well as being able to monitor the changes that are happening today.
Hello, my name is Kate Underhill and I'm a rocket scientist with the European Space Agency. I studied physics and space engineering back home in the UK, and now I'm based in Paris at ESA's Space Transportation Directorate. And today I'm going to be answering questions from all over Europe about rockets. So let's see what our first question is. Could you describe a rocket launch step by step? To start at the beginning, at least for ESA's rockets Ariane and Vega, many parts of the rocket are built in Europe, from all over Europe, and then shipped across the Atlantic Ocean to Europe's spaceport in French Guiana. French Guiana is a really good place for a launch base because we've got lots of room to do our activities, because it's on the coast of South America, so we can launch over the ocean and not over people's heads, because there is not many earthquakes down there, so we don't have to worry about them shaking up our rockets, and because it's near the equator. And with the Earth's rotation every day, that means that our rockets are already going at 1,500 kilometers an hour before they even take off. So all the parts of the rocket are shipped down to French Guiana from Europe. Some parts are built there, are made there, like the solid boosters of Ariane 5 or the first stage of Vega. Then the satellites we're taking into space are built all over the world and flown into French Guiana, and we assemble all these elements together. Put the rocket bits together, put the satellite on the rocket, and then we put a protective cover on the satellite called a fairing. Now there are so many bits of a rocket because a rocket is made in stages. And why we have stages is because to get into space, a rocket needs to be going really fast. It needs to be going at nearly and over 8 kilometers a second. In order to do this, we have to burn a lot of fuel. But the more fuel we burn, the heavier the rocket is, and the harder it is for the rocket to get off the ground in the first place. So we do it in stages. A stage is ignited, it burns up all its fuel, and then as soon as the stage is empty, it drops back down to the ground, and the rest of the rocket, the other stages, keeps going up into space. And we do this in as many stages as we need until we get up to the final speed we want. Now this staging principle is shown by this animal-tastic graphic of a Vega rocket. A Vega can take the equivalent of a hippo into space, a satellite of up to 1.5 tons. Now, once we're in space, and to get the hippo, our satellite, to exactly the right position, we need 0.5 tons, or a polar bear's worth of fuel in the last stage. Now, to get that polar bear and that hippo up through the top part of the atmosphere and into space, we need 2 elephants worth of fuel, 11 tons of fuel. To get 2 elephants, a polar bear and a hippo up through most of the atmosphere, we need a Camarasaurus worth of fuel, 24 tons. And to get a Camarasaurus, 2 elephants, a polar bear and a hippo off the ground in the first place, we need a huge amount of fuel and a huge amount of power. We need 88 tons of blue whales worth of fuel. That's nearly 300 times more fuel in the big first stage that takes us off the ground than the light top stage that maneuvers us in space. We have built the rocket together, we've assembled the stages, we've checked everything is right, we're happy with the rocket, we take it out to launch pad, then we get the green for the final countdown. 3, 2, 1, liftoff. The first stage engines ignites and the rocket takes off in a boom of noise and light. So the rocket flies up on a trajectory or a path to space that we've predefined for it. It goes vertical at the beginning and then lifts over horizontal in a maneuver we call a gravity turn. It rushes through the atmosphere, and then as soon as out of the atmosphere, we can drop the protective fairing around the satellites because there's no more air drag on them. Then it keeps flying upwards, dropping stages, each time one of them is empty of fuel, and then eventually getting to space and getting to position where it releases the satellites into the places they need to be, and then the final stage of the rocket will maneuver itself into a safe orbit to avoid any kind of collisions with any other spacecraft. So let's see what our second question is. How fast can a rocket go? Now this is a really great question, because how fast a rocket goes is linked to what the satellite is going to do that it's taking into space. So for example, Europe's Ariane 5 took the automated transfer vehicle, the ATV, to space so it could deliver supplies to the International Space Station. In order to get to the space station, Ariane 5 gave the ATV a speed of 7 kilometers a second. The ATV was 20 tons at liftoff. If we want to go a bit further up, so for example, geostationary orbit where all the telecommunication satellites are, 36,000 kilometers up, then the rocket needs to give that satellite 9 kilometers a second to what we call a geostationary transfer orbit that will set it on the path to its final destination. Ariane 5 can take 12 tons up to 9 kilometers a second. If you want to go even further, so to the moon for example, then we want to go on what we call a lunar transfer orbit, again on the path towards the moon. And to put a satellite on a lunar transfer orbit, then the rocket needs to be going at over 10.5 kilometers a second. And this is what Europe's new rocket, Ariane 6, will be doing when it delivers a lunar lander around the moon. Now if we want to go even further, we have escape orbit. This means leaving the gravitational attraction of the Earth and going out into the solar system. In order to reach an escape orbit, the rocket needs to be going at 11 kilometers a second. This is exactly the speed that Europe's Ariane 5 gave the Rosetta Comet Chaser mission back when it launched it in 2004. Ariane Rosetta was only 3 tons at launch. And so for our last question, I'm being helped by Tom here. Tom, what's the last question? Can a rocket lift off from another planet? This is another great question. And the answer is yes, of course it can. And in fact, we've already done it. When the United States landed on the moon over 50 years ago, the craft they landed on was in 2 parts. One part that stayed on the moon, the second part lifted them off the moon and into orbit and back home to Earth. This is what I love about rocket science and about science in general, is the same rules apply everywhere. The rules we have today for designing and building rockets apply wherever you want to launch from. All you need to know is that the heavier the planet you're on is, the harder it is to get into space. But to make all these ideas a reality, to launch from Mars, to make our own propellants, we need new rocket scientists like Tom here and like you to make these ideas a reality.
My name is Yves Doat. I am an operation engineer working for the European Space Agency. A spacecraft can be a satellite orbiting a planet or an object, or a vehicle traveling through the solar system. The spacecraft control depends on the control center, a network of antennas distributed around the Earth, a communication network connecting the control center to the antennas, and of course, the communication between the antennas and the spacecraft for sending command and receiving telemetry. Earth observation missions are flying South Pole to the North Pole, back down to the South Pole, and again the North Pole. And as you can see, with each orbit the spacecraft will fly above a different region of the Earth. Where do I put my antenna? Very simple. The best location will be either the North Pole or the South Pole. Geostationary spacecraft are flying above the Earth, above the equator, at an altitude of 36,000 kilometers. At this altitude, the spacecraft will make a turn around the Earth in 24 hours, which is exactly the same speed as the Earth's rotation. So always in visibility of the same point on the Earth. In that case, antenna can be located in the north hemisphere or in the south hemisphere. In the case of deep space, the spacecraft will fly far away from the Earth. And you can see, in that case, while the Earth is rotating, the spacecraft remains practically at the same position. So we will need several antennas around the Earth, and their location will ensure the correct coverage of the mission. And in that way, we have a nice coverage of our missions, deep space or around the Earth.
My name is René Wittmann and I work as a spacecraft operations engineer for ESA's program mission in Ritu. Of course I believe that satellites will become more autonomous. PROBA stands for Project for Onboard Autonomy, and our mission's main goal is to demonstrate that satellites are able of controlling themselves. They do so today, much in the same way as a self-driving car. You still need to decide where you want to go, and you need a driver. But on the highway, the car will run on its own. For our satellites, this means nominal operations are taken care of by the satellite. You don't need an operator to command the instruments. However, in case of anomalies, you still need the team to investigate what went wrong. Let's take PROBA V as an example. The mission constantly monitors the health of plants on Earth. To do this, it takes photos when flying above the land. For an older mission, you would have to calculate when the satellite is in the sun and flying over an interesting area and program the camera to turn on and off again. PROBA V takes care of this all by itself. It is equipped with GPS receivers similar to the ones in your smartphone and a so-called land CMOS. That is a special kind of map that allows the satellite to determine if it is flying above land or ocean and accordingly turn cameras on and off by itself. Well, the truth is, even though satellites are highly developed machines flying in space, they're still just a computer and not able to cope with the unknown all by themselves. In case of an anomaly, you need a team of experts on ground to investigate and find a solution for the problem, and in the best cases, we even manage to reprogram the satellite and mission control system to resolve the same problem automatically in the future, thus still improving the autonomy of the satellite.
Hello, my name is Armel Hubo and I'm a spacecraft operations engineer at the European Space Operations Center in Darmstadt, Germany. Well, the first step is to receive a message, a report from our Space Debris Office telling us that we risk a collision. It will tell us exactly at what time it's going to happen, the chances for this to happen, is it 1 over 100, 1 over 1000, and it will tell us the near-miss distance. Are we going to fly as close as a few tens of meters, a few kilometers? And this is important information, because with it, we decide if we want to do a maneuver or not. Another thing which is important to know is what the other object is. Is it a space debris, in which case it's easy, we just do the maneuver, or is it another live spacecraft? This is a bit more tricky, because in this case, chances are that the other satellites will also know that we're coming and will also try to avoid us. And if everyone is doing a maneuver at the same time, we do not want to both move to the same place and risk a collision again. The idea is that either we move away from each other, or only one of the two is moving away. So this is something that we have to discuss with the other agency, with the people who are flying the other spacecraft. And once it has been decided that we are the ones who are going to move, we need to ask our colleagues from navigation, the experts who calculate the trajectory and the maneuvers of spacecraft, to do a calculation for this maneuver, which means how long are we going to fire the thrusters and in which direction. And then once this is done, we also need to check the new orbit in which we're going to move. Are there going to be space debris there? Because if we move from a dangerous orbit into an even more dangerous one, then we have gained nothing. So when we have all this information, once we are sure that the new trajectory is good, we uplink the commands to the spacecraft, we perform the maneuver, verify that it executed as planned, and then we're done.
Hi everyone, my name is Pete Collins and I work for ESA at the European Space Operations Centre in Darmstadt in Germany. This is Gaia right here, or at least a model of her. Just over 2 years ago, we had a problem. We had a big anomaly in flight where we had a failure of an onboard unit. We actually had a failure of some of the electronics inside. And she was able to notice that she had a problem, and she switched to her redundant units, her backup units on board, and said, this unit's broken, I'm not going to use it anymore. When she did that though, that meant that she wasn't able to carry on the normal mission. She wasn't able to carry on doing the science mission that she was designed for. So that's where the team that I work on came in, the flight control team, of which I'm a part. And we came in and we had to figure out what the problem was and how to fix it in the short term to get the science mission running again. The problem with that is it's not like going to fix a broken car or something like that, where you can actually go and touch it, you can use the screwdrivers, you can open the bonnet, you can have a look. With Gaia, she's quite a long way away. She's 1.5 million kilometers away, so it takes 5 seconds for a signal to Gaia to reach us on Earth. So they were a bit limited, and we have to look at the data coming from Gaia being sent through space to ground. We look at things like temperatures, voltages, currents, data from other sensors. And we did this as a team, and we discussed together, and we were able to fairly quickly understand what happened and bring Gaia back to full performance, performing her science again. And we were able to do this within a couple of days. So it was a really intense period. We were working long hours. The most interesting bit for me was, as well as the technical details, was the coming together of everybody and the teamwork of these many different people and many different organisations, all working in different parts of the world. It's a privilege to work for ESA because one of the great things is its distribution of people and the different types of people from different backgrounds and all coming together to work together. And that was, for me, one of the main achievements of this critical phase that I've just spoken to you about.
Hello, my name is Nicole Kaplan and I'm a research fellow in astrobiology at ESA. I'm going to answer some of your questions about this exciting field of space science. When astrobiologists talk about the limits of life, we're referring to the known boundaries that life on Earth, so life as we know it, can survive. These physical and chemical conditions include temperature, radiation, water availability, and toxicity of metals in the environment, to name a few. We all know that different living organisms have different requirements for these things. For example, you and I need around 8 glasses of water a day, but that's going to be quite different for, say, a fruit fly or a cactus. Did you know that there are some life forms that can actually survive periods of time without water? You might think of a camel with its water-storing hump on its back. But if you think smaller, much smaller, there are some microorganisms that can survive complete desiccation. And this means that they can be totally dried out and go into a dormant or sleeping state. They can wake up again once they're hydrated with water. Microbial life dominate all sorts of extreme environments. The current world champion for upper temperatures for life on our planet is a strain of archaea, found in a hydrothermal vent. It's known as strain 121. Any idea why it was called that? Maybe you already guessed. It is able to survive and even reproduce at 121 degrees Celsius. And it's this sort of life, which we call extremophile life, that astrobiologists are interested in to support theories of panspermia, where microorganisms might have needed to survive long trips around our galaxy on comets or asteroids to go and bring life to planetary bodies, perhaps including our very own home planet. In the same way that life is transferred around different habitats on planet Earth, you might like to consider that space can also act as one big system, and life is a part of it. And in some ways, that's already true. Have you ever seen a shooting star? Meteor showers are common and can be observed from many parts of the world. We already know that there has been, and still is, an exchange of materials between Earth and Mars, because we have evidence from Martian meteorites that landed here. Space is such an active place, so it's quite possible that some life forms hitched a ride from one planet to another. The difficulty is that such a ride would be impossible for you or me, because of the extreme conditions. That's why astrobiologists are studying many types of microscopic extremophiles to test out their limits and to see if maybe life was imported here from somewhere else in space. If we're planning on exploring other planets or icy moons that we think may contain or once contained life, then how do we make sure that we don't contaminate it? It's a very important thing to consider. The Committee on Space Research, COSPAR, has formulated a planetary protection policy to define different destinations in space and allocate them with appropriate levels of protection. For example, the Sun is in a category which says it's not of interest for life detection missions. So we don't have to put in special measures to make sure that we're not going to contaminate it. But it's a different story for Mars or other planets we think might harbour life. ESA has adopted this policy and acts on behalf of its member states to ensure that the requirements are met for all missions the agency is flying to or contributing to. By employing the use of clean rooms for our spacecraft and following strict sterilisation protocols, we can minimise the risk of contaminating other places and explore space in a considered way.
Hi, my name's Kate Isaac. I'm a physicist and I work at ESTEC, which is in the Netherlands, and it's the technical centre of the European Space Agency. I work on a science mission called CHAOPS. CHAOPS stands for Characterising Exoplanet Satellite, and what we're going to do is to measure very precisely the sizes of exoplanets that have been found by other people. The Earth, Mars, Jupiter and Mercury are all planets that go around or orbit the Sun, which is our star. These are 4 of the 8 planets in our solar system. An exoplanet is a planet that is outside our solar system. It is typically orbiting a star, although it doesn't have to be. As of July 2020, we know of more than 4,000 exoplanets that have been discovered in searches that have taken place both from the ground and from space, using space missions that are operating above the Earth. These searches have found many unexpected types of exoplanets and have produced many surprises. Many planets that are very different from those that we are familiar with. Planets much smaller than the Earth, larger than Jupiter, the most massive planet in our solar system, also the largest, as well as planets that are much hotter and much colder than anything we have in our solar system. Planets with temperatures higher than molten lava inside a volcano and higher than the melting point of iron. The first exoplanet discovered orbiting a star similar to our own Sun was discovered in 1995 from the ground. 51 Peg b has a mass of about half that of Jupiter, but that's where the similarity stops. It's orbiting a star called 51 Pegasi, which is reasonably bright as stars go, but still not quite bright enough to be seen by our own eyes when we look up at the sky. The planet has an orbital period of just over 4 days. This compares with an orbital period of the Earth, which is 365 days or 1 Earth year. So 1 year on 51 Peg b is much, much shorter than that on the Earth. The planet is much closer to the star, which means that the planet is very hot. It is in fact more than 4 times hotter than the Earth is. Although to date we have found more than 4,000 exoplanets, we still haven't found one that is exactly like our own Earth. We are continuing to look, of course, but in the meantime we're trying hard to understand more about what we've already found, about the exoplanets that we've discovered to date. We ask ourselves, what are they made of? Are they rocky? Are they icy? Are they big balls of gas? Also, what we would like to know, and what we're interested in finding out, is how they were born and how they age, as well as whether they have atmospheres like our own Earth. All the time we're thinking in the back of our minds whether there is an exoplanet out there where in the future we could possibly look for and find signs of life. Travelling to an exoplanet is not possible today, as even the nearest ones are much too far away. It would take light more than 4 years to travel from the Earth to the nearest exoplanet we know of, which is in the Proxima Centauri star system. As of today, we can only travel at a very small fraction of the speed of light, and it would take us tens of thousands of years to reach the exoplanet. This is much longer than a human lifetime, much longer than the lifetimes of many human generations, in fact.
Hi, I am Nicola De Quattro and I'm the Head of Engineering and Innovation at Vitrosys at Belgium. Today I'm going to talk about satellite navigation. A global navigation satellite system, or GNSS, is formed by a constellation of satellites like this beautiful Lego model and a ground system spread over the world. The user on the ground, like our smartphones or the navigator in our cars, receives the signal that is transmitted constantly by every satellite on the Earth, and from some specific parameters of this signal is able to determine the position on the ground. Every big countries in the world, they have their own satellite navigation system, like USA, Russia, China, Japan, India, and of course Europe with the new Galileo system. Although the process of computing the position is in practice very complex, you can imagine measuring the distance of yourself and all satellites with a rope. And from all these measurements, your navigator is able to determine your position on ground. And this is possible wherever you are, in Europe or in China, or on a mountain, on the sea, in a sunny day or in a stormy or in a cloudy day. The only thing that you need is to see a portion of the sky. Of course, you want the navigation to be precise enough. You don't want your navigator to bring you off-road because it told you were in a completely different place. For this reason, the ground system plays a really critical role. It measures the quality of the signals that is transmitted by the satellites by means of antennas which are spread all over the world. And then corrections are computed and sent periodically to the satellites. Now, of course, the GNSS in general is much more than that. Galileo, for example, the European satellite system, for example, provides services for precise timing with an outstanding precision, or supports search and rescue systems for localizing people in trouble and allow them to ask for help. Also, it supports European governments by providing services which have a very high precision for sensitive applications. Satellite navigation is nowadays very important for our daily life, and you are using it more often than you can think. Have you ever sent your location through WhatsApp? Or have you ever shared the place you are through Facebook? And have you ever wondered how Pokemon Go could know where you are and where the Pokemon are? Also, the most obvious application there is road navigation, which allows you to visit your friends or a delivery truck driver to find your place. But we are so used to navigation with smartphones that for us navigating with a paper map or reading the road signs to understand our position or finding the route is really a distant memory. And can you imagine what it's like to navigate in the sea, where your only reference is the stars and a paper map? Now, all ships in the world today, they use GNSS to navigate. But GNSS is very important, especially in emergency. If you are, for example, a skier and you are hit by an avalanche, or if you have lost your path through the mountains, or if your boat is broken, then navigation is the only way you have to let people know where you are so that you can be rescued. Losing the satellite navigation services for just one day would then create an enormous damage to our lives, even just losing it for one day. Of course, we cannot repair satellites, we can repair ground equipment. For this reason, all the components of the ground are constantly monitored and maintained. Every day we experiment the benefits of satellite navigation, but this is just the beginning. Now, if navigation is very precise and reliable, why should you look at your navigator and steer the wheels of your cars if you could just let it do it for you, just relying on navigation information? The delivery of packages could happen through cars or drones without the need of a driver, directly to your home. Robots could autonomously patrol our cities for improving our safety. Now, this seems like far future, right? Actually, this is something we are really close to do. But in order to do that, we need to continue improving satellite navigation. And this is mainly for two reasons. The first one is that we would really literally put our lives in the hands of an electronic system. And this is a tremendous challenge because failure will not be an option anymore. Secondly, there are men out there which have learned how to steal our systems, how to break into our smartphones, and they could, for example, steal our packages or even really bring us off-road, just penetrating into our navigators. So these are the highest priorities today for future innovation. And I have a question for you. What about the Moon and Mars then? Well, astronauts will need to navigate over the Moon and over Mars, and they would need, sooner or later, a satellite navigation system for them. And this is one of the most exciting and great challenges of the next future.
Hello everybody, my name is Martin Azkarate. I work as a robotics engineer in ESA, in the ESTEC establishment in the Netherlands, and I want to talk to you about space robotics. So my role in ESA is to develop different robotics technologies for space applications, and in particular I focus on planetary exploration, like the Martian rovers that you probably heard of. And part of my work is to do research and development in the Planetary Robotics Lab, where I am now, and to develop lab rover prototypes like the one you see here behind me. So looking at the sky from Earth, we find robotics applications in one of the lowest orbiting satellites, the International Space Station, where we have robotic arms that help and support the astronauts in their tasks and activities and allow them to perform some activities that it would be very difficult to conduct otherwise. From there, and going higher in altitude, we find also robotic applications in the servicing of satellites. And there is this very hot topic and interesting topic nowadays that is called the active debris removal, and the use of robotics in order to capture a satellite and deorbit it whenever this satellite becomes non-operational anymore. Going farther away from Earth, we find also robotic examples in planetary exploration, like the cases that have reached the Moon or Mars, with landers and rovers that reach these locations. And even farther away, we can also mention the very famous example of the Rosetta mission, where the Philae probe landed in a comet and allowed us to perform some science in situ in the surface of this comet. People tend to ask me whether if robotics exploration will eventually replace human exploration. And actually the answer is very simple, because this is somehow already happening, but I wouldn't say that robotics replaces humans. I would say that robotics is a precursor for humans. Robotics missions nowadays allow us to reach distant and very unknown areas that it would be very difficult and actually very risky to reach by humans directly. Because of the environments that we can find there can be very harsh and very difficult to cope with by humans. So robotics are providing us nowadays very, very useful data, very useful information and knowledge about the environments and conditions that we can find in the solar system planets, so that we can even think of sending humans later on whenever the technologies and the astronauts are actually ready for it. A very good example of robotics missions serving as precursors for humans are the Martian rovers, actually. Like the ExoMars mission that will be launched by ESA in 2022. These missions are allowing us to perform a lot of very interesting science in situ in the surface of Mars and discover many things about the geology, the biology, the meteorology of Mars. And these missions to Mars may eventually allow us even to bring an actual soil sample of the Martian terrain back to Earth. You probably want to know what are the key functionalities that these Mars rovers need to embark in order to accomplish their missions. So actually, each of these rover missions have their own scientific objectives, and this science is the one that is actually driving the design of these rovers. But I would like to first mention the case of the ExoMars rover, and what makes this mission unique and this rover very special is the very complex drill system that it will embark. And this system will allow it to perform sampling operations that go down to 2 meters below the surface of Mars and acquire soil samples that are protected from the cosmic radiation that reaches the Mars atmosphere by these first 2 meters of layer of bedrock. This is something that no rover has tried before, and that's why we are so excited about it in ESA. The second example I would like to mention is the upcoming ESA rover mission to Mars, the Sample Fetch Rover mission, or SFR, which is part of the Mars Sample Return program in collaboration with NASA. The objective of this mission is to collect and bring back to the lander some samples that have been previously taken and strategically dropped by the Perseverance rover, the one that was recently launched by NASA. What this SFR rover will need to embark in order to accomplish this mission is actually a lot of autonomy. Actually, it will need to traverse very fast and autonomously, and also autonomously fetch all these samples that finds along the way. And in order to accomplish this, it will use mainly the stereo camera sensor in order to localize itself as it moves, and also to model the environment and detect the obstacles that it finds on the way in order to find safe paths that allow it to reach the target locations where these samples are. So that was all from the Planetary Robotics Lab today. And if you have any other questions, please feel free to contact me and I will be happy to answer them.
Hello, I'm Jason Hatton. I'm responsible for the coordination of biology and exobiology in the SciSpace team of the Human Spaceflight and Robotic Exploration Program. So I'd like to give you a little bit of an overview of the research that we do using ISS. So the International Space Station, as its name suggests, is international, and basically it allows you to do very long duration experiments in the spaceflight environment. So looking at the effect of microgravity, low gravity, also exposure to the direct space environment. You can do research in all fields. You can study, of course, the astronauts, how they react to the space environment. So studying the changes in their physiology. You can study biology. So the cells, which would be cells from, say, human body, microbes, plants. You can study also physical sciences, materials science, fluid physics, and also, of course, you can look outside from the space station. You can look at the Earth, so you can do Earth observation. You can do also observation of the space environment. Nice thing is, because it's an international platform, all of the facilities, all of the instrumentation is shared. So that allows you then to do a lot of research and very internationally. So there's been about 3,000 experiments done over the lifetime of ISS. And those gave about 2,000 scientific publications. One of the areas, of course, of interest is astrobiology. Do microorganisms or microscopic animals in dormant state, can they survive exposure to the space environment? This is very important to see whether life could be transported from one planet to another on astronaut, or whether also if you have, for instance, microbes on a spacecraft going from the Earth to Mars, how do you prevent contamination? The other aspect is also, how did life originate? So there's a lot of studies on the chemistry which led to life, so which may have been going on the primitive Earth or on the surface of a comet. So we developed an instrument called EXPOSE, and this was put on the outside of ISS and allowed exposure to direct space environment for typically 18 months, 2 years. And what was found was, in fact, that many of the microbes and even simple animals such as tardigrades, these are water bears, could actually survive direct exposure to the space environment for 18 months or so. And so that was a very interesting finding. The other area, of course, is plant biology. And there was actually a whole series of experiments done over a 10-year period by a team of European and US scientists. And they looked at all sorts of aspects of plant biology. They looked at how plants responded to gravity, because what you can do on board of the ISS is you can effectively look at what happens in the absence of gravity, and you can apply, using a centrifuge, artificial gravity, and then see what is the perception threshold for plants to gravity. And that was actually found to be, hundreds of normal Earth's gravity, so plants are very sensitive. One of the experiments which was particularly nice was an experiment which studied a process called circummutation. So when a plant grows, if you look very carefully, it doesn't just go straight up, it does a sort of circular motion. And with this circular motion, this was actually observed by Charles Darwin. Although he observed this, he couldn't figure out what the mechanism was. You always have gravity on the Earth, but going to the space station, it was possible to do an experiment where we could take away gravity, we could apply gravity, we could turn the light on and off, and answer this question. In fact, what it was found was it is internally driven, but it's very strongly affected in terms of the period and the intensity by gravity and by light. So that was a very nice result, answering a question that Charles Darwin had posed over 100 years earlier. A lot of the research which is done on board of ISS is basic research, but it has relevance to a number of applications. Material science, for instance, you can do much more precise measurements. Also research which is relevant to health. Right while I'm standing here, my body is working against gravity. And of course, in spaceflight, in microgravity conditions, you don't have that. So what happens is, unless you do exercise or some kind of countermeasures, so that could also be with diet, you will lose a lot of your bone and muscle mass. And this actually parallels some of the changes which occur when people are very inactive, so sitting at the desk, or in the elderly also have trouble with mobility. So you can look at, say, the transfer between the techniques you use to as what we call countermeasures against bone and muscle loss for astronauts, and what you would do for people on the Earth who also have problems with bone and muscle loss. You can also do research with things such as nematode worms. So there's small microscopic worms. They also have muscles, and they lose muscle mass in spaceflight. And it turns out that the genes which control the muscle proteins and the muscle growth are actually very similar to the genes which humans have. So you can actually study you can manipulate that process, and that gives you some clues into the mechanism. So there's a whole series of experiments which have been done on that. The final thing is, of course, if you're going to Mars, you either take a lot of tinned food with you, or you grow your own food during the mission to Mars, and also perhaps to regenerate your atmosphere, converting CO2 back into oxygen. So there's a project we have called Melissa, which is a bioregenerative life support system. So it has plants in there, it has algae in a bioreactor, it also has a waste treatment system. So all of the technology which goes into that also has applications on the Earth. If you want to do agriculture in a very intensive environment, so in a greenhouse, you want to do that very reliably. So that's also an area where there's transfers. So there's many different transfers of knowledge which are possible.
Hi, my name is Tia Flem-Detlefsen, and I work for the European Space Agency. Today I would like to tell you a bit about space law. Just like on Earth, we have laws in outer space that tells us what states are allowed to do. These laws were made at the United Nations Committee for the Peaceful Uses of Outer Space, and they were made to make sure that space was used for peaceful purposes and for the benefit of all humankind. The main treaty is called the Outer Space Treaty, and it says that everyone shall have access to use and explore outer space as long as they follow the rules in the Space Treaty and in international law in general. That means that states are not allowed to send up weapons of mass destruction into outer space, and they may also not harmfully contaminate another planet. The Astronaut Rescue and Return Agreement says that states shall render all possible assistance to an astronaut in distress. We also have a liability convention because, just like on Earth, if an accident occurs, we want to know who is liable for the damages. The liability convention tells us that if the accident occurs in outer space, we have to look at who is at fault. The registration convention says that states shall register their space objects. This way, we can have a better overview over the man-made activities in outer space. And finally, we have the Moon Agreement. It has some principles about how we should conduct our activities in outer space. However, one of the concepts is a bit controversial, called the common heritage of mankind, about how we should manage and own the moon. Therefore, no spacefaring nation has ratified this agreement. Have you ever watched a clip of the first moon landing, where Neil Armstrong and Buzz Aldrin planted the American flag on the moon? Maybe you thought about what this meant, because back in the day when you planted a flag, it indicated that this new territory was yours. However, no one owns outer space, so planting your flag there won't have this effect. That's because Article 2 of the Outer Space Treaty says that outer space is not subject to national appropriation by sovereignty, by means of use or occupation, or by any other means. Article 1 says that outer space is the province of all mankind. So, if you go to outer space, you're not allowed to bring back your own souvenir because space belongs to all of us. Astronauts are also not allowed to own their own space souvenir. But what other laws would apply if we imagine that they live in an international moon base? If we imagine that the moon base consists of different modules and that each member state had their own module, then it would be the national law of that member state where, for example, a criminal activity is conducted that would apply on board that module. Now, if we compare the International Moon Base to the International Space Station, then we can imagine that member states would like to make a similar intergovernmental agreement where they agree on how they shall conduct their activities on board, and it would include principles such as peaceful uses and international collaboration. Now, when the astronauts go outside of the moon base and onto the lunar soil, it will be the same space treaties that I was talking about earlier that would apply. That means that if an astronaut wants to conduct a scientific experiment, they have to make sure that they do not interfere with the activities of other astronauts, both current and in the future. It also means that if a criminal activity occurs outside the base, then it would be international criminal law that we also know from Earth that would apply. When we go somewhere new and we have to build a new base, then the easiest way is to use the materials that is already there instead of having to bring everything with you from home. This is especially true when we're talking about distances to the moon. Here we can use space resources such as dust and rocks to use as construction. And if you would like to know more about this, then you can check out the ESA educational video on space resources. Now, for the legal side of it, what we're looking at is how to regulate it so that all states have a fair and equal access to space resources, and that it's done in a sustainable way.
Hello everyone, I am Charlotte Goetz. I am a scientist at the European Space Agency, and I study comets and how they interact with the space around them. What is a comet? Comets are small objects in our solar system. They're usually just a couple of kilometers in diameter. It's about the size of a village or a small city. And they are made up of ice and dust. This ice and dust is very, very loosely packed, so there's a lot of small spaces in between it. This means the density is quite low. So if you had a really big bathtub, the comet would actually float in it. They also have very small gravitational pull. So if you jump on a comet, just a little bit, you would just float away. Comets have all kinds of shapes. Most of the ones that we've seen are kind of potato-shaped. But my favorite, this one, and it's kind of rubber ducky shaped. They hurtle through our solar system at speeds about 1,000 times faster than you can go in a car. So this is about 1 to 100 kilometers per second. And the ones that we know most are those that go closer to the sun. There, the comet then heats up because of the sunlight on its surface, and the ices become a gas and leave the comet. They expand into space. And this causes the gases to be accelerated away from the comet, which then forms a tail. And this is what most comets are known for. Some of these tails are so bright that by just looking at the night sky with a small telescope or binoculars, you can actually observe these tails yourself. Where do comets come from? About 4 billion years ago, our solar system didn't exist. None of the planets in it had formed. There was just a giant nebula around the sun that was made up of ice and dust. And the planets then started to slowly form and started to collect the nebula around them. But small rocky beginnings of comets also formed, and they very, very slowly collided together. Some of them continued to grow and became moons and planets, but some of them were just small, didn't grow much further, and eventually they moved out to the edge of our solar system. Passing planet or even a passing galaxy from outside our solar system can give them really tiny push, and they start to journey back into our solar system near the planets and near Earth. And this is where we can observe comets as well. Because these comets have up until then had a very quiet and undisturbed life, they haven't been heated up by the sun, They have very small gravitation, though they're not compressed by their own gravitation. And that means that these comets are actually the leftovers that we can observe from the formation of our solar system. They can tell the story of what this formation period, this time where the planets formed and the moons around them actually looked like. So we can understand how the solar system was made by looking at comets. Can we visit a comet? Yes. Well, not we ourselves, but we can send little robots, spacecraft, to the comet to observe it for us. The first major comet that we were able to observe with spacecraft was Comet Halley in 1986. It was visited by a fleet of little robots from all over the world, from the United States, from Russia, from Japan, and also from Europe. They observed the comet, but only very briefly. They couldn't stay there. That's much too difficult for such a fast comet as Halley. But they flew by in a couple of hours and they collected all the data that we can then analyze. This helped us see what comets look like, the shape, and what the dust was like that surrounded it. But the scientists wanted to study a comet in more detail and over a longer time to see how it evolves from being very far away from the sun to very close to the sun. So in 2014, the European mission Rosetta arrived at Comet 67P Churyumov-Gerasimenko, and it was able to stay there for 2 years and observe the comet and its surroundings. And Rosetta's little sibling, Philae, even landed on the comet and took pictures just a couple of centimeters from the surface. This was quite an achievement for a little spacecraft that's just the size of a washing machine. At the end of the coming decade, so at the end of the 2020s, we're going to launch another cometary mission. It's called Comet Interceptor, and it will be the first spacecraft ever to fly by a comet that has just come from the edge of our solar system. This mission will tell us how comets change as they approach the sun, and it will help us understand our own planet Earth and how the solar system formed.
System engineering and testing are important aspects of a satellite mission. Components are tested separately and then together once they're integrated. But how many tests is a good number of tests? Let's ask satellite engineer Cristina del Castillo. Cristina, thank you for joining us.
To you, Leyland.
So can you tell us what you do at ESA?
So I work as a satellite system engineer at the education office, and I support university students who are undertaking a CubeSat mission, and I support them from the design phase to the testing and then finally to the operations.
Can you tell us what system engineering is and how you can apply that to a CanSat?
So system engineering in general is a toolbox that we typically apply in space missions, and it consists in breaking down a mission objective into several different levels of decomposition, and we typically use it to go from one mission statement until a final product, and it involves different steps of interacting with persons and interacting with the design and the testing. So if I were part of a CanSat team, how I would apply system engineering would be by first tackling and analyzing the mission objective, and then trying to see what functions I need in my CanSat so that I can fulfill that mission objective. But what is important is not only to select these components that you are going to use, but to also see how they interact with each other and how the different elements of the CanSat interact with each other. So once you have come to a design, what is important is that you ensure that you can verify that these functions that you need there are actually there in your present design, and that's when testing comes in hand, because this is when you start trying and tinkering with the different elements of the CanSat until you can finally verify that it's actually meeting the objectives that it was intended to do.
How do system engineers interact with other experts to ensure that their part of the mission is fulfilled?
So the role of a system engineer is also to ensure that the right information is with the right people at the right time. So you need to ensure that, for example, if you are working on the electrical system in the CanSat, that the other team members know that you are the type of components you are using. So if there are changes in the design, this should be flow down to other disciplines, and communication shall be done between the different disciplines. So the role of the system engineer is to ensure coherence within the system and ensure that everybody can have the access to the information they need to perform their duties and their tasks.
Which aspects of satellite testing would you apply to a CanSat?
So in general, testing a spacecraft compared to testing a CanSat is different, because the conditions that we see in space are much different than the conditions that we see on Earth, thermal conditions or microgravity conditions. That is why it's sometimes very difficult to test a spacecraft on Earth. So what we do is we break down the critical functions and analyze what critical environments they need to be subject to, so that we can check that this function works in a certain environment. So if you think of a CanSat mission, I would start by looking at the different phases of the mission and check what are the critical functions at the different points. And then I would recreate an environment that allows the team to test these functions. For example, if you have a sensor that you know it needs to work at a certain speed or velocity conditions, perhaps it's a good idea to test this sensor in that type of conditions, so that later when it's used on the real mission, on the campaign day, you know for sure it's going to work.
Christina, do you have any advice for CanSat teams that have experienced failure?
First thing I would tell them is not to worry, because failing is part of the learning experience, and they will certainly learn a lot from their failure. But second, I would like to give them an advice, and is if you fear that your mission is going to fail, you can do some things to prevent, and this is actually what we typically do in spacecraft missions. We design the satellites considering the possibility that they can fail, and by inserting some design changes, we can actually try to prevent this failure. So what I would recommend to a CanSat team is that they sit down and they try to analyze at what points or at what components their CanSat mission can fail. By trying to prevent this, it's maybe possible that they will actually prevent this failure and will have a successful launch campaign.
Thank you very much, Christina. Good luck to CanSat teams, and remember, design a system that can be tested, tested, tested. Satellites can do anything these days thanks to sensors, electronics, and onboard processing. But putting it all together can be a bit of a puzzle. Onboard computer engineer Gianluca Ferrano joins us to help think about how to piece things together. Gianluca, thank you for joining us.
And thanks for having me here.
Can you tell us a little bit about what you do at ESA?
I'm here in ESA, in Aztec, since 20 years, and I've always been into the data systems division, where we do digital electronics, not only onboard computers, for all these missions, ranging from science to Earth observation to experimental missions.
So what are the differences in onboard processing in space versus on Earth?
Embedded systems in space and Earth have a big difference in terms of the type of components we are allowed to use. Everybody now is used to have very large performance possibility on their mobile phones, while in space we have components that lag behind the terrestrial counterpart by several generations. So in space we have to cope with an unforgiving environment, vacuum, radiation, vibrations, tiny resources, very little power in general, very little possibility to dissipate heat. All these things together means that we have to squeeze every drop of performance from very old devices, delivering extremely robust systems. It's not an easy job, but it's part of the fun.
And what about specifically for CanSats on Earth?
I believe CanSat are a very good way to understand the limitations and the challenges of designing embedded system for space. You are limited in resources, first of all in volume, in power, limited in type of components you can use, but the concepts are the same. And the good thing that, especially nowadays, that also some of the components that you can use are basically the same. I'm thinking of the most common embedded system platforms like Arduino or Raspberry Pi that now have also space-grade counterparts. And so whatever is done on a CanSat is conceptually similar to what we do on grown-up systems. So it's a very good gym for people who want to learn the specific of embedded system for a safety-critical system, not only for space.
How would you structure the onboard electronics of a CanSat to take failures into account?
Failures is what we design around in space embedded system. Is what said in the past, failure is not an option. Failure is not an option only if you take failure into account in all your design processes. For example, you need to understand that a particular component can fail because of an inner failure. Failure can be triggered by an environmental situation, temperature too hot, vibration, shock, and you need to have a backup function or a backup component for some of this component. Example, the CanSat use the RF link to download the data. Maybe it's a good idea to have a copy of the data on an internal memory. And CanSat have a battery. Maybe it's a good idea to have a backup battery that powers just a part of the system. All those things need to be evaluated depending on the system you are designing. And you need to have not only complete redundant system, so a second memory if the first fails, but also a possibility of graceful degradation of your performances to save something of your mission if things go wrong. So you might not get all the data, but you get some of the data, or at least you get an information why the mission failed. The new paradigm in space, especially in new space, is to fly fast, fail fast, and redo it. You learn from this process only if you have all the information why a system has failed.
Do you have any coding tips for CanSat students?
Software is as important as hardware in this process, especially now that hardware systems become more and more miniaturized and concentrated in single chips. And there are ways to do software well and ways to do software wrong. The same things that I said about the hardware, you need to have processes, redundant processes, is applicable to software as well. For example, systems can have watchdogs that checks that a certain process that didn't get stuck while running and can be restarted from another watchdog process. This is a common technique. There are several of those safe software techniques that are also extremely important because are the same used not only in space, but in a lot of safety critical systems on ground. And this makes the CanSat exercise more interesting because whatever a student learns there is applicable in medical system, in automotive, in safety critical industrial system, and this is extremely important.
Thanks a lot, Gianluca.
Thanks to you.
And good reminder for students that there's a lot to be learned from failure, so don't be afraid of it.
Designing a CanSat is a super achievement, but teams must be able to communicate with their satellite during its mission. Radio communications is an important way of sending and receiving data. Paolo Concati is a system engineer specializing in communications, and he joins us to talk about talking with our satellite. Hi, Paolo. Thanks for joining us.
Hey, thank you for inviting me.
Can you tell us a little bit about what you do at ESA?
Well, each ESA mission need to have this data exchange to perform the work. So there are always radio that are needed to receive the command and send back the information and how the satellite is doing. So my work here is for the missions I follow to ensure that we define, build, and have the radio that those missions need. That's my job.
And is radio the only way to communicate with a satellite?
Well, radio is the way to access your satellite. So you have to have this means no matter what, and radio is the only way so far to reach the satellite. When you're on ground, you have many cables that goes back and forth because you want to see what is going on inside. But once your satellite is wheeled and working and has to fly, radio is the only way to do it from remote. There are other ways that are coming, that is these optical communications, but they are very difficult to be handled and they need to have clear skies. So they are very tight conditions to do it. So radio is the only way that allows us, no matter what, to have access to the satellite.
And what about for a CanSat?
Well, those optical links are really big and power hungry. So today I don't see anything that can fit in a CanSat, but you never know. With good technology development, maybe one day there can be something that can squeeze in a CanSat.
Is it possible to speak with a satellite that's farther away from Earth, or perhaps that's even left our solar system?
Well, it is kind of being like at a party. There is a lot of people talking, there's a lot of noise, but if you're close by, it's easy. But this does not mean that you cannot reach a friend that is further away. You start screaming. That's when we boost the satellite signal with high power, or when you start steering at the people. This is our directive antenna. So it's possible, but it's more difficult. It's the same problem. We just need to have more resources, more power, bigger antenna. But yeah, and actually, it's already done. NASA has a couple of very old missions that keep flying and flying. And yeah, they're exchanging data from very far away, out of the solar system.
So what antenna should CanSat students use to be sure that they receive their data?
Well, first of all, you need to consider the fact that you have the space segment, the CanSat, and the ground segment, your ground antenna. So the CanSat may be lost in altitude or may not be able to point always toward you. So you should consider an antenna that can provide you access to the data without having the need to point perfectly toward the ground antenna. So think about something that is like a patch antenna or a small dipole, so something that is not directive. When it comes to ground, if you're able to say where the CanSat is, you can have something that is more effective on a specific direction, so has gain, like a Yagi antenna or a small parabolic antenna. But consider the fact that, for example, a Yagi antenna, the more element you have, the stronger is the signal, but the less aperture antenna provides. So you have to be more precise in pointing. So find the right trade-off between the performance and the robustness of your link. So in general, be careful with not only the performance, but also what the antenna is to provide. Performance versus coverage.
And finally, do you have any other advice for CanSat students as far as setting up the radio communication?
Well, I would say the advice is the same for somebody that is going to deep space. Keep it simple and stupid. This is the only way you have to access the satellite. Do not introduce unnecessary complications. They may come with problems that you may discover in space when it's too late to fix it. So yes, simple.
Thank you very much. You guys heard it from Paolo. When it comes to radio communications for your CanSat, keep it simple.
A CanSat needs to land safely to ensure a successful overall mission, and a parachute is a way of ensuring that. But how does a parachute work, and what are some things to keep in mind when designing yours? I'm joined by Luca Ferrancina, an aerodynamics engineer, to tell us more. Hi Luca, thanks for joining us.
You're welcome.
Can you start off by telling us a little bit about what you do at ESA?
I'm part of the aerothermodynamics and flight vehicle engineering section. I've been working most of the time dealing with spacecraft entering at very high speed the atmosphere, whether it is the atmosphere of Earth or Mars or Venus. So dealing with the heating that is produced, the stability of the capsules, And then I moved to the descent part, looking at the parachute. So I spent almost 10 years now working with parachutes. And recently I became the technical responsible for the parachute of ExoMars.
So can a parachute work anywhere in space? What would happen to a parachute on another planet, for instance?
Well, parachutes are aerodynamics devices, so they need air. Okay? The drag that the parachute generates is the same drag that you need to overcome when you launch the spacecraft, and you simply use it on your benefit. You have different types of parachute. You have the most common ones, the one that you have under your seat when you fly with an airplane. You have the ones that the military use to be dropped on the front line. But there are parachutes which has much more demanding application. Parachute which are used for recovering part of rockets. The space shuttle use parachute to recover the rocket booster. The Ariane 5 rocket booster has been recovered with parachutes. The astronaut coming back from the ISS use a system of parachute. The astronaut coming back from the moon use a parachute system to land on the ocean. You even have parachute for mission coming back from asteroid. The Stardust, Genesis from NASA, the Hayabusa from JAXA, all use parachute to retrieve the capsule and safely land on ground. But even more exotic, you can use parachute to go to other planets. We have used parachute to go to Mars, to Venus, to Jupiter, to Titan. So all this has been using parachute because there was an atmosphere. If you do not have an atmosphere, obviously you need to use a different system like a propulsion system. When you land on the moon and there is no atmosphere, you cannot use a parachute.
So what would be an alternative recovery system to a parachute?
But depending on the condition. So if you are still in an atmospheric environment, so you can have different systems than the parachute. You can have deployable, you can have inflatable. You need to realize that the way the parachute generates drag is essentially exposing a surface to the flow. The bigger is the surface, the faster you slow down. So if you are still in the atmosphere, you can have devices like deployable and inflatable that simply increase the area which are exposed to the flow. So you open up panels, you increase the size, and then you have the system to brake. But it's obviously only if you have an atmosphere. If you don't have an atmosphere, again, it doesn't always work. You need to have a propulsion system, for example. In any case, the parachute is part of the solution, and in some cases, as I said, it is not the solution at all. If you go to Mars, you reach the atmosphere of Mars at 5-6 kilometers per second. If you come back from Mars, you hit the atmospheres of Earth at velocity up to 13 kilometers per second, and you do not deploy a parachute at those velocity. You need to wait until you slow down, and then only when the spacecraft has reached lower velocity you can open the parachute. Usually you have to wait until you are subsonic, and then you open the parachute. Sometimes you don't have the time. You simply need to open the parachute as soon as possible. When you go to Mars, you're approaching the ground very fast, and you end up opening the parachute while you are still traveling twice as fast the speed of sound. As soon as you have opened the parachute, then, which is the most difficult part, then you slow down. The remaining velocity maybe is still compatible with your system. Otherwise, if you need to remove also that part of the velocity, you might use a propulsion system to land. You can use airbag, crushable structures, and then you are safely on the land.
So what are some aspects to keep in mind when designing a parachute?
Maybe it's easier if we go quickly through the design process. First of all, you need a parachute to slow down. So how much do you need to slow down? maybe you have a system that doesn't need to slow down that fast. It's sufficiently robust that when you hit the ground, it doesn't break. So in certain conditions, you don't even need the parachute, okay? But suppose that you need the parachute, okay? How fast are you allowed to touch the ground? Maybe you are carrying something which is very delicate and you want gently touch the ground. Or maybe you can allow the system to have a much higher velocity when you hit the ground. Now, you need to realize that as soon as you open the parachute, you start generating drag, okay? At a certain point, the drag is equal to the gravitational force. And then when they are equal, essentially you start falling at a fixed velocity, which is the terminal velocity. So the first question is, what is the terminal velocity that your system is allowed? The bigger the parachute, the lower is the terminal velocity. So the first thing that you need to start figure out is how big is the parachute. As soon as you have the size of the parachute, then you need to decide how strong it needs to be. And once again, the most difficult part for the parachute is the instant when the parachute gets open, when it gets inflated. Only at those specific instants, the parachute is stressed. The load on the parachute are the maximum. So you need to find out what are these stresses, these loads, to figure out how strong the parachute needs to be and which material you need to use to sustain those stresses. So then you have the design, you have the size, you know the material, you can build the parachute. But at that point, you are probably not even halfway of your solution, because you have the parachute, but you need to bring the parachute inside the spacecraft. And most important, you need to find a way to get the parachute out of your spacecraft. What you do usually is you pack very compactly in a specific manner of folding the parachute into the bag. There is a specific bag designed for containing the parachute. But then you need to find a way to get the bag out of the spacecraft. And here you have different options. You have a simple system like you have certain panels of the spacecraft which are left and removed, and while they're flying away, they pull out the bag. You have small rockets which are fired and they pull out the bag. You have a smaller parachute that pull out the big parachute. Or more classically, you have a cannon, essentially. You have a mortar which explodes and literally shoot the parachute out of the spacecraft. And then the parachute immediately inflates. So now you have the parachute, you have the way to put it inside, and you have the way to shoot it outside. So you are almost there. What is remaining is to be sure that the parachute works as you think it should. And in parachute business, testing is a really essential component. And despite the fact that you do testing and you do verification only at the very last moment, you need to start thinking about this at the very beginning. You might have a lot of time, you might have a lot of money. Probably you will not have both. More realistically, you have none of the two. But still, you need to figure out how much testing you need to do. Maybe you can do testing only of specific aspect. At a certain point, you might do different sizes because you cannot afford to do full sizes. You might not afford to do it at the right speed. You might not afford it to be 100% representative. If you think about, if you want to be sure that the parachute for Mars works on Mars, you need to do a test on Mars, which is clearly not feasible. So you might end up in doing the verification step by step, looking only at a certain aspect. And for what you cannot verify, you need to take margin to cover the risk and to guarantee that everything works.
Sounds like quite a challenge. Thank you very much for answering our questions today. Best of luck to CanSat participants as they design their own parachutes. So you've participated in CanSat, and now you want to take your satellite design skills to the next level. What programs are out there, and what should you keep in mind? Alexander Kinnaird is the Engineering Program Coordinator for University Student Activities, and he's here to tell us how CanSat students can scale up their missions. Hi Alex, thanks for joining us. Can you tell us a little bit about what you do at ESA?
Yeah, so as you said, I'm the Engineering Program Coordinator for University Student Activities. And what that means is I work with students at universities who want to design, build, test, and then launch and operate experiments or satellites. And I normally work with experiments which are flown on stratospheric balloons or on sounding rockets. And I'm also the program coordinator for a program called Fly Your Satellite, which is for CubeSats, which are very small 10 by 10 by 10 centimeter satellites.
Can you tell us how designing a CanSat might be similar to designing an experiment for a sounding rocket or a stratospheric balloon?
I think it's pretty similar. So when you're designing a CanSat, your students will know that they have to think about the constraints that they have. So your CanSat's only a certain size, you only have so much room where you can put your electronics, where you can put your experiment, and you're only allowed a certain mass for your launch vehicle. And then you have things like to consider like power, where you're going to get the power from, how much power you're going to use. And it's similar on the rockets and the balloons. So we have a certain size of the rocket where you can put your experiment, there's a certain mass you're allowed, and the same one. And you also have to think about what the functions of your experiment are going to be. So what it is you want to achieve, and then you can design everything, you start to put it together, and in the end you have to test. And testing is one of the most important parts as well. So I think with the CanSats you're also doing tests, with Rexus and Vectus, and with the Flyer satellite, testing is a big part of the program.
Would you be able to put a CanSat on a sounding rocket and a stratospheric balloon, or is a CanSat too small for those platforms?
No, you can, of course. I'm sure the students know there's an awful lot you can do with miniaturized electronics. Things get smaller and smaller all the time, and you can do an awful lot with that. So on Rexus, we already have so-called free-falling units, things that we throw out of the rocket that perform experiments during free fall. On the balloon, not so much, but you can also have things like CanSat sizes which stay with the vehicle. So I know your CanSats are launched from quite a low altitude, maybe a few hundred meters or a kilometer. Rexus normally goes to something like 70 or 80 kilometers. Vexus goes to 30 kilometers. So you can imagine if you throw a CanSat from one of these vehicles, it's got a long way it can go, especially when you open the parachute. It's a big challenge if you want to launch something from one of our vehicles and then find it again. So what a lot of experimenters choose to do is stay with the vehicle. And I think that's probably the best way to do your science.
So what are the technical differences for experiments that are designed for a sounding rocket versus a stratospheric balloon?
Yeah, there's a difference, right? So if you think about a rocket, you're sat there on the launch pad, everything's quite a nice environment, but then very quickly you have the rocket ignition, you're going to accelerate very fast. There's a lot of G-forces, there's a lot of acceleration, a lot of noise, a lot of vibration, but the journey's not so long. So for a sounding rocket, you can expect to fly for between 3 and 10 minutes. You have all the noisy environment, but then you have a lower pressure environment and maybe a low gravity environment as well, if your rocket is despun. And you have to design your experiment to survive all of this, but not for very long. The balloon's quite different. The balloon flights are very long. They can take 1.5 hours to get to the top, to the apogee, and they fly for maybe 3 to 5 hours up there. So when you're at 30 kilometers, you have low pressure, you have low temperature, and you have to think about how you're going to power your experiment for that duration. So there's some similarities because the atmosphere at 30 kilometers is similar to the atmosphere at 70 kilometers, but the duration and the way you get there is quite different, and you have to design your experiment for those different platforms.
What advice do you have for CanSat students interested in someday launching a CubeSat?
Well, I think keep it up. If you've been building and working on CanSats, you've got a great experience. You've done hands-on engineering, you've been doing system engineering, you've been doing electronics. You need to keep up these skills, also with projects in general. So buy the Raspberry Pis that control the lights in your house. Stay in the clubs in school and outside of school where you build race cars and build model rockets. And then when you go to university or further education, join the clubs. There's going to be lots of other people who are also interested in science, technology, engineering, and space. If you join these clubs, you can form teams. Other people are interested in space, other people may be interested in CubeSats, and then maybe one day, I'll see you here at STech with an application for the Flyer satellite program.
Thank you very much. As Alex said, we hope to see you one day taking part in one of ESA Academy's hands-on projects. Time in space as we know it started with a bang. What did the early universe look like immediately after the Big Bang? And how did that lead to us? I'm Leylaan from ESA Education, and we're at the European Space Agency's Technical Center in the Netherlands to learn more about our cosmic history. From the Big Bang to the early stars and galaxies, we need to speak to an astronomer to find out more. Hi.
Hi, hello. My name is Rachna Vatodekar. I am a research fellow here at ESA. And before I started working at ESA, I did a PhD in astronomy from the University of Nottingham back in the UK. And even before that, I'm an engineer originally.
So you're an astronomer engineer. It sounds like the perfect person to ask about the early universe. So can you tell us what the early universe looked like?
Sure. So our universe formed in an event or in an explosion known as the Big Bang some 13.8 billion years ago. And just within a second after that, the universe was filled with small particles such as the electrons, protons, and neutrons. But because the universe was an unimaginably hot place right after the Big Bang, it was not possible for these particles to actually come together to form atoms. But then the universe continued to expand and cool down such that after about 400,000 years, when the temperature had dropped down to about 3,000 degrees, it became possible for these particles to come together to form neutral atoms, atoms of hydrogen and helium. And these hydrogen and helium, they were the first elements to form in the universe.
So when did the first stars and galaxies come to be?
So right after these very first elements, that is hydrogen and helium, were formed, there was a period in the history of our universe, something that we astronomers refer to as dark ages. And as the name suggests, I mean, the reason we call these period as dark ages is because there was essentially no source of light. The first stars and first galaxies, they were not born yet. And so the universe was predominantly composed of these dark clouds of hydrogen and helium. And so these dark ages lasted for about 100 million years or so, and only after that the small dense clouds of hydrogen and helium, they started collapsing under the influence of their own gravity, becoming hot enough to kind of trigger the nuclear fusion reactions within them, and this led to the formation of the very first stars and first galaxies. So nuclear fusion essentially is that when two lightweight atoms are forced together to form a heavier atom, and a lot of energy is produced as a result.
And that energy is the light that we see.
Exactly, that is the light and the heat that we see from our own sun. That is exactly how it is formed.
We've often heard this expression that we are all made of stardust. How's that possible?
The light and the heat that we see from our sun, it is made through a process called as nuclear fusion. And all the elements that make up our human body, such as oxygen, carbon, nitrogen, phosphorus, and sulfur, they were created in stars through the very same process of nuclear fusion. At the end of their lives, stars swell up, they expand, and they explode in massive cosmic explosions known as supernova. And when supernova explode, they expel all the material they have produced, including the very elements that make up our own planet and even us. So essentially, because all of us are carrying the remnants of these distant massive supernova explosions within our own bodies, we say that we are made of stardust.
The James Webb Space Telescope is often referred to as a time machine. How's that possible? How can it transport us so far back in time?
Because light takes time to travel from one place to another, we see objects not as they are now, but as they were when they emitted the light that has traveled across the universe to us. So for example, the light from the sun takes about 8 minutes to reach us. So when we are looking at sun, we are looking at it not as it is now, but as it was 8 minutes ago. Similarly, the nearest neighboring galaxy, Andromeda, it is 2.5 million light years away. So when we are looking at Andromeda, we are looking at it as it was 2.5 million years ago. So essentially, all the telescopes are time machines, but the James Webb Space Telescope, or the JWST, it's going to take us the furthest back yet. So if I have to put things in perspective, The Hubble Space Telescope that we have now, it is the most powerful telescope, and with it we have been able to discover galaxies as far back as 13.4 billion years ago. This was when the universe was just 400 million years old. But the James Webb Space Telescope, it has been designed to peer the universe even further than that, to find the first stars and first galaxies when the universe was just 200 million years old.
So we're talking about baby photos of the early universe.
Baby photos of the early universe, precisely, yeah.
Cool. When it comes to stars and galaxies, which one came first? Do we know?
We don't know that yet. All we know that is the very first sources of light, they came after the dark ages, as I explained earlier, so about 150 million years after the Big Bang. So yeah, I'm very much excited and looking forward to work on the data from JWST very soon.
Yeah, we hope to see it soon as well.
Fingers crossed.
Yeah. Thank you so much for speaking to us today.
No problem. This was so much fun. Thank you so much.
Most of us can picture a telescope, typically a long tube mounted on a tripod. Telescopes come in all shapes and sizes, and they're some of the most powerful machines in the world and in space. But how do they work? I'm Leilan from ESA Education, and today we're asking an ESA expert working on the James Webb Space Telescope. Welcome to our little studio.
Thank you very much.
Dr. Giovanna Giardino, thank you for being with us today.
Thank you for the opportunity. I'm very excited.
So what do you do at ESA?
So I'm an astronomer and I work for ESA on the Webb Space Telescope.
I think a lot of people envision a telescope like my childhood telescope, yes. So it's sort of this tube. Yes. And even the Hubble Space Telescope is what everyone pictures as a telescope, this kind of giant tube in space. Yes. How does a telescope work?
So in very simple words, a telescope, it's a bit of a bucket of light, bucket of photons. So using a lens of a mirror that is inside this tube, you collect the photons, the light from an object and concentrate it, focus it in a specific point so that you have much more signal, much more light for that object that you would have with your naked eyes. And that way you can see far away objects, weak signals.
But then you have the James Webb Space Telescope that looks completely different, and yet it's still a telescope.
Sure.
Why does it have such a unique design?
The main elements of a telescope are really the mirrors or the lens that you use to collect the lights and focus it, right? So that's what you have to have. The tube is that we see in many telescopes that we use on the Earth as mainly two functions. One is the holding of the lenses, the lenses that you need, or the mirrors. So you have to have a structure that keeps them in the place and with the right distance from each other. That's very important for focusing. Going for the tube allows you to block off extra light from the surrounding that you don't want to come into the lenses and disturb the clear vision that you have on the sky. It also keeps it clean, right? In the environment every day there is dust and things, so the tube keeps it clean.
So the fact that James Webb Space Telescope doesn't have this giant tube, how is its structure being held together? How is it remaining clean?
Right. So the structure is held together. So by the primary mirror is mounted on the spacecraft, and then there is, if you notice, a tripod going off from the primary mirror to what we call the secondary mirror, right? And the light gets into the primary mirror, the big bucket that I call, right? Get focused on the secondary mirror, and then focused again into the primary focus of the telescope where the instruments are, and we actually collect the lights and look at it in a camera or a spectrograph. So the camera, it's really a camera. So like the name says, we record images. So the telescope collects the light, focuses, and this camera collects it and records. So we see images, we can see the stars, nebulas. And the spectrograph, the light entering a spectrograph is dispersed with a prism, or we also use gratings, but the principle is the same. The idea is to disperse the light and look at the components of the light. So like when you have invisible light and you shine it through a prism, you see the colors coming through. No, that's the spectra of the light. These are the components of the white light, the red, blue, yellow, that's the component. And the same we can do in the near infrared, and in the infrared, and we look at the components. And why do we do that?
Good question.
Yeah, because in a way, the light that an object emits, it's a bit the signature of the object. It tells us a lot of what the object is made of, which elements are present, what temperature, what the pressure, what the physical condition.
And then what about the famed honeycomb mirrors? Why is it a honeycomb? What's the structure?
Right. So, as you know, the Webb Space Telescope is one of the largest telescope ever launched. It's 6.5 meters in diameter, the primary mirror. Even the primary mirror would not fit in any of the fairing of existing launchers. The diameter is about 3 meters. So the design has to be such that it could be folded for the launch to be fit into the rocket.
And I suppose the honeycomb structure is what really allows you to be able to fulfill that.
Right, the honeycomb, so that you want a continuous surface, right? You don't want gaps. So the hexagonal, as the bees have discovered, it's a very efficient way to tile a surface and also give it a rounded shape. You could do that with squares, but then you end up with a square telescope, which is not ideal to focus the light.
So the honeycomb mirrors are not just in a honeycomb shape, but they're also this beautiful yellow gold color.
That's
what material are they made out of?
Each of them is covered by a very thin layer of gold.
And why gold?
Why gold? Because gold is the ideal reflector in the infrared. So for infrared, for a normal visible light, we often use silver or aluminium, right? It reflects very well in your mirror. Mm-hmm. But in the infrared light, gold performs better.
Okay. And that's sort of this
That's
outer
the surface.
Surface layer.
The technology behind each of these hexagonal segments was developed especially for the Webb Space Telescope to make a large mirror that is light. So the material of beryllium was selected to make the structure that you see under the gold coating. And beryllium is very strong, very stiff. It's got good properties when you cool it down, it's stable, but at the same time it's a light material. So we could make a large telescope that is not too heavy and can be launched in space.
So you mentioned earlier a sun shield.
Yes.
Can we talk about the sort of structure of the sun shield as well and its purpose?
Yeah, the sun shield is very crucial on this mission. It was very challenging to design such a huge sun shield, 5 layers of special material as big as a tennis court. So obviously will not fit in any of their existing rocket. Mm-hmm. So it was designed to be in a compact configuration and folded around the primary mirror at launch, so that it could fit in the fairing of the Ariane 5 rocket. And the reason it's there, it's because the Webb Space Telescope, it's optimized for observation in the near infrared, in the near and mid-infrared part of the electromagnetic spectrum.
That's the light that we can't see with our eyes.
Exactly. And that's the reason of the sun shield, to keep the telescope and the instruments, the scientific instruments, always in the shade of the sun and the Earth. The space is very cold. It's minus 270 degrees. So by keeping the telescope always in the shade of the sun, we can cool it down to very low temperature, minus 220, 230 degrees Celsius, really cold. And that it's great to observe infrared light, because then we have a very sensitive instrument.
And how many detectors are on James Webb Space
So
Telescope?
there are 4 scientific instruments with different function for different type of science that you can do. NIRSPEC, the near-infrared spectrograph, MIRI, the mid-infrared instrument, NIRCam, the near-infrared camera, and NIRIS, imager and spectrograph.
Okay.
Yeah.
And what are you hoping that information will tell us about distant galaxies, just the early stars?
We see objects that are 13 billion light years away from us. We expect to detect these. So it means that we're going to see objects as they were 13 billion years ago. So these are the very young galaxies. So we want to know what was going on there. What was temperature? What was the pressure? How many stars? And we can do that with a spectrograph, exactly analyzing the light. And then learn how the galaxy formed by looking at these very young galaxies. Yeah. If we come closer to home, we can also look, for instance, at the atmospheres of planets in our solar system, Jupiter, Saturn. Again with a spectrograph, learn what's going on this.
And Webb
planets.
will be looking at planets as well.
Yes, planets in our solar system, and also planets that we call exoplanets, which are planets that orbit stars in the galaxies.
Do you think James Webb Space Telescope will help us discover life on other planets?
That is a difficult question. Life per se, I think it will be difficult. I think it's not really something very likely. But because of this capability of looking at the atmosphere of exoplanets, and also, for instance, the moon of Jupiter's, I think we could learn a lot about whether the elements are present that could sustain life. So if we look at the planets, that it's what we call the habitable zone. So at the right distance from its own stars to have temperature that are not crazy cold or crazy hot, right? So that's a temperature range that we think, okay, life could exist. And then we look at the atmospheres. And for instance, we see that there is oxygen, there is water vapor, there's methane. That could give us a hint that life is present or it's possible on that planet. So that's very exciting.
Wow, Giovanna, thank you. That was a lot of information, but I think it might be helpful if we went and saw the model of the James Webb Space Telescope.
Yeah, sure,
Should we do that?
Of course, let's do that. Okay.
Let's go take a look at this model.
Yes.
Wow. That is incredible.
Yeah.
Wow.
Yes.
It's quite impressive, even at this size.
It is. It's a very striking shape, right?
Giovanna, thank you so much for talking to us today.
It's been a pleasure.
It's really inspiring that a little girl who looked up at the stars in her hometown ended up working on the world's most powerful space telescope.
Yeah, it's very exciting and was very fortunate. Yeah.
Thank you so much.
Thank you. Thank you for the opportunity to talk to you.
If you're looking for more astronomy educational resources, check out ESA Education's Teach with Astronomy webpage, and keep an eye out for more videos coming from ESA Education. To look up at the sky on a dark, clear night is a jaw-dropping and humbling experience. It makes you wonder where we fit in all of this. I'm Leilan from ESA Education, and today we're going to speak to an ESA astronomer to find out more about our place in the universe. Teresa Irapkova. Did I say that right?
Yes, you said it perfectly.
Welcome. Thank you for joining us today.
Thank you for having me. I'm really happy to be here.
So what do you do at ESA?
I work at ESA as a research fellow, which means 100% of my time is dedicated to do research. And I work on star formation. So I'm trying to understand how stars form, how they evolved, and in which groups they are forming. If we, for example, can see some star clusters, how they evolve.
How did you understand our place in the universe, like where the Earth is in the solar system?
If we look at the solar system, we live on Earth, but there are other planets as well. Some of them are closer, some of them are bigger, some of them also have moon, Some of them have actually many more moons. And with all of this, we orbit around Sun. There are also smaller objects called asteroids and minor planets. And they are all over the solar system. There are also very distant objects in a Kuiper belt that actually are on a very different orbits and can become a comet when they come close to the Sun. So in order to understand the scales a bit better, as a ruler, we can use the speed of light and how long it would take the line to travel from different parts of solar system. So if we are on Earth, it would take us 1 second to reach the Moon. It takes 8 minutes to get to the Sun, and it would take more than 4 hours to reach the outer parts of the solar system. So maybe in a sort of more common analogy, we could see that our solar system fits into one house, then the outer parts of it would be the garden. And then we would like to visit our closest neighbor, which would be the closest star to the Sun. So it would take us with the same velocity, the speed of light, around 4 years. And that's the closest star to us. And then there are billions of other stars, billions of other houses that actually create a galaxy. And they are not randomly distributed, but they are villages. These can be small star clusters, but there are also really big cities. And these would be more massive and more dense star clusters. And the centers that are the densest, you can see it as the downtown area of a big cities with the high tower houses with lots of apartments in them.
And then these different cities, they would form sort of states and countries. These would be galaxies.
Yeah, exactly. So if a city would be star cluster, then indeed we could distinguish the galaxy from a star cluster in a way as we have cities and states, because they are different objects.
Typically, astronomers use telescopes to take pictures, that also give us measurements. But how is it that we can understand how heavy a star is or how fast it's moving from an object that we can't actually put on a scale and weigh?
This is a very good question, and maybe I can come up with another analogy in this way. So the thing is how actually we study stars. Stars are born, then they evolve, they age in a similar way as we do, and then they die. But we just can take pictures. So how does this work? So the way we can study stars would be similar in earthly matters. If we would get a task, imagine that you are at school and the teacher tells you, okay, you have now 1 hour to learn about dogs, everything you can, but you cannot use internet or anything. You have just 1 hour, and I want you to figure out what dogs they are, how can you determine how much they weigh and what's their age. So you can then quickly take your bike and a camera and run all over the city and take as many pictures of dogs as possible. Then you come back to the classroom and then you can have a look at the pictures. And then there will be pictures of number of dogs playing in the groups, like stars and star clusters. And then some of these dogs will be alone, and some of them are big, and some of them are small. But you face all of the problems that, for example, you have 2 small dogs. One is a puppy, because puppies are small, because when a dog is born, it's small. But they're also a small breed. So it can be older Chihuahua, for example. And then you need to come up with the features, how to actually distinguish whether it's a puppy or Chihuahua. Okay. So then your estimate of the mass, just based on the information, would be different. And this is a type of research that actually we do in astronomy. We take all of these pictures and then we try to see, okay, this star is similar like Sun. It has a similar light, so probably it will weigh the same as Sun.
Teresa, why do we care about the size of a star, about its weight, about how fast it spins in a galaxy that's billions of light years away from us?
That's a great question. And actually, when I now think about it, we did always cared. I would say that we can define astronomy as a field that is studying every object that we can see at the sky. So it can be sun, it can be planets, but also other stars and galaxies. It was actually crucial for our survival. So, for example, when we started travel on the sea and the ocean in between the continents, we needed stars for the navigation, otherwise we would always get lost. In addition, the knowledge of seasons and tides and the weather in general was crucial to harvest and create food. So actually, all of the astronomy in general and the knowledge of celestial bodies helped us to create a society that we have today.
Now, is astronomy something you were always inspired by as a kid, or what was your path to astronomy?
I was actually born in a small village in the mountains, so I did lots of sports. I did skiing, I played football, and I was not really thinking about any scientific career or anything for a very long time. Only just before, when I had to decide what high school I'm going to go, I realized, oh wow, it's actually, I need to do something else than just running around in the forest. So I was thinking what I should do. I vividly remember one moment when I was just looking at the books and I was thinking where to start, and the one book that I opened was Problems in Mathematics. And I said, okay, so I will sit down and try to focus. So there was this one problem that I thought is probably difficult, but I sat down and I read the problem and I thought about it a bit, and then suddenly I knew how to solve it, and I solved it and I checked and the answer was correct, and it felt really satisfying. So I thought, okay, maybe this is something I want to do.
Thank you so much, Teresa, for speaking to us about our place in the universe.
Thank you for having me.
If you're looking for more astronomy educational resources, check out ESA Education's Teach with Astronomy webpage, and keep an eye out for more videos coming from ESA Education.
Hi, my name is Nora Lützgendorf and I'm an astronomer at the European Space Agency. Today I want to talk about light and the electromagnetic spectrum. First of all, what is light? Light, or visible light, is just one part of electromagnetic radiation. This kind of radiation can be seen as a wave, similar to the wave that you see when you throw in a stone in a lake, or a very fast particle that moves with the speed of light. But for today, we're just going to be talking about the wave character. So visible light is everything you see around you. It comes from the light inside your house or the light from the sun. You sometimes even see it split up in its components, the different colors, when you look at a rainbow. Our eyes are only equipped to see visible light, but there is actually so much more to the electromagnetic spectrum than this. Let's take the wavelength of the visible light, for example. This wavelength is in the order of 100 nanometers. This is as big as the point of a needle or maybe a single-cell organism. If you make that wavelength even smaller, to the size of a molecule, you get what we call ultraviolet light. You cannot see that light, but it would probably look very violet. It is the light that actually produces vitamin D in our skin and makes our skin tan. It comes from the sun, but again, we cannot see it. Now making this wavelength even smaller, to the size of an atom, then we get what we call X-ray radiation. You have seen this before in your doctor's office, because X-ray radiation can actually go through our skin and reveal our bones. Making it even smaller than this, so 100 times smaller than an atom, to make it to the size of the core of an atom, you will get gamma ray radiation. Gamma ray radiation is very energetic radiation, which we don't see very often on Earth, but we have seen it in the universe. Very big events such as supermassive black holes merging can produce gamma ray radiation. Now let's go to the other side of the spectrum. Let's make the wavelength bigger. If we make it as big as a blood cell, or maybe even the thickness of a hair, we get what we call infrared radiation. Infrared radiation is also called heat radiation. You might have seen it when you look at the heat camera and you see which body parts are hot and which are cold. All bodies in the universe actually emit heat radiation. It doesn't matter if they're cold or hot. And we cannot see this radiation either, but sometimes we can feel it. Making it bigger, to the size of an insect, going from 3 millimeters to 30 centimeters, we are coming into the regime of the microwave radiation. You have something like this in your own kitchen. A microwave uses microwave radiation to heat up water. Making it bigger than this, going to the biggest wavelengths that we have in the electromagnetic spectrum, going to 100 meters and bigger, it's what we call radio radiation. Those are such long wavelengths that they are able to travel very, very far and undisturbed. And that's why we use this a lot for communication. Radio radiation can be transmitted and also received from those really big radio dishes that you often see. Now you have seen that light is only one small part of the electromagnetic spectrum. So if we observe the universe only in the visible light, we wouldn't see much. We would only see a very small part of the universe. Luckily, we have developed instruments and telescopes that can observe the universe in different wavelengths. Those different parts of the electromagnetic spectrum reveal different parts of the universe. Take infrared, for example. Because of the size of the wavelength of the visible light, which is about the same size as the dust particles in our universe, visible light cannot go through dust because it will be absorbed and scattered by those dust particles. However, if you have longer wavelengths, such as the infrared, they can go through dust unnoticed. This is the reason why telescopes that observe in the visible, such as the Hubble Space Telescope, gave us those amazing images. But whenever you observe a dust lane, you would see just a dark spot on the image. Telescopes that observe in the infrared, such as this James Webb Space Telescope, will be able to look what's behind this dust. This is really important for objects such as supermassive black holes in the centers of galaxies because they sit behind big dust lanes, but also for the birthplaces of stars and planets who sit in dust and gas clouds that they were formed of. Out in space, away from the hot and busy Earth, the James Webb Space Telescope will be able to observe a whole new world for astronomers in the infrared.